We live inside a river whose current we almost never question. Time sweeps us forward in a steady and silent motion, one heartbeat after another, one sunrise folding into the next. To us it feels constant, like an invisible drumbeat that has always been there and will always remain. You wake to the chime of an alarm clock, and in that small sound is a trust that every second is equal to the one before it. A farmer measuring the seasons by the return of the rains, a sailor once navigating by the rising of the stars, a physicist listening to the steady tick of an atomic clock, all share the same underlying belief. Time is absolute, unshakable, impartial. It does not speed or stumble. It does not care whether you are rich or poor, awake or dreaming. To the human mind, time has been the most reliable companion of existence. The ancients saw time as divine. They saw it as a gift from the gods, or as an eternal order written into the cosmos. In Babylon, priests recorded the motions of planets to track omens, convinced that time itself carried messages from beyond. The Egyptians built obelisks that cast shadows across the sand, trusting the regularity of the sun's path to mark the hours of each day. The Greeks gave time a face and a name. Kronos was the father who devoured his children, the eternal devourer of moments. In all these cultures, time was not imagined as flexible or fragile. It was imagined as the spine of reality, the skeleton on which the flesh of events hung. This view of time as rigid persisted into the scientific age. When Isaac Newton peered into the fabric of nature, he saw a clockwork universe governed by simple laws. For Newton, gravity pulled planets in orbits as predictable as gears, and those motions unfolded within a stage called absolute time. To Newton, absolute time was universal. It flowed equally everywhere in the cosmos, indifferent to motion, indifferent to gravity, indifferent to matter itself. Every second in his universe was the twin of every other, identical and immutable. Newton wrote of it as something that existed in its own right, flowing steadily whether or not any events filled it. It was the silent metronome of the universe. And to be fair, Newton's vision worked spectacularly well. His mathematics described the fall of an apple and the arc of a cannonball, the tides stirred by the moon, and the orbits of the planets. For centuries, nobody had reason to doubt the constancy of time. It matched common sense, it matched experience, and it matched the success of prediction. Time simply was. To challenge that view seemed almost absurd, but the human mind is never content with certainties. As the 19th century closed, physicists faced cracks in Newton's perfect clockwork. Light itself refused to fit the mold. No matter how you chased it, the speed of light refused to change. Whether the Earth was moving toward a star or away from it, light raced past at the same measured pace. It was as if time and space themselves were conspiring to protect this single constant. Then, in the early 20th century, Albert Einstein dared to ask the unthinkable. What if Newton had been wrong about time? What if time was not an absolute drumbeat at all? What if time could bend, stretch, and twist, depending on how you moved or where you stood? Einstein's revolution was not just a mathematical trick. It was a profound shift in how we imagine reality. He showed that time is tied to space, forming a single fabric we now call space-time. He showed that motion could alter the flow of time. Two clocks moving differently would not agree when reunited. He revealed that the heartbeat of the universe is not a single metronome, but a chorus of ticking rhythms, each unique to its path through space-time. And yet, Einstein's boldest claim still loomed. He suggested that gravity itself, that invisible pull that binds us to the Earth and holds the planets in orbit around the Sun, was not just a force acting across distance. Gravity was a warping of space-time itself. And if space-time is the stage on which time flows, then gravity must have the power to bend not only space, but also time. It is a claim that sounds almost like myth. To say that standing on a mountaintop changes the rhythm of your life, to say that living close to the Earth's core slows your clock, to say that near a black hole time itself can grind nearly to a halt. These are not the words of everyday experience, and yet they are the truth written in the mathematics of relativity and tested again and again by experiment. We take the flow of time for granted, trusting it as the one thing beyond question. But that trust is misplaced. The river of time is not uniform. It bends under the weight of gravity, it stretches under the influence of motion, and it fractures our naive sense of reality. Einstein revealed that what we call time is not divine, not absolute, not eternal, in the way the ancients believed. It is flexible, fragile, and woven into the very geometry of the universe. And so the question rises like a whisper through the centuries. If time is not constant, why should gravity, of all things, slow it down? Time is so woven into our lives that we barely pause to notice how strange it is. We carry clocks on our wrists, in our phones, in the very satellites that circle the Earth. We trust them to keep our days ordered, to tell us when to meet a friend or when to send a spacecraft toward another planet. Yet behind every tick of a second is an assumption that each beat is equal to the last, that time does not bend. Imagine a pair of lovers separated by oceans, staring at the same moon. They believe they live in the same present moment, connected by the same unfolding of seconds. To human eyes and hearts, this seems unquestionable, but beneath that belief lies a hidden fragility. Even the ancients sensed time's mystery, though they clothed it in myth and ritual. The Maya charted cycles of the heavens with breathtaking precision, recording centuries of eclipses and alignments, convinced that time itself was circular, destined to repeat. The Hindus spoke of kalpas, great ages in which universes are born and destroyed, immense scales where human lifetimes are less than the flicker of a candle. To them, time was divine, immeasurable by human means, stretching far beyond comprehension. These visions, though poetic, still carried the sense that time was a cosmic order, a truth beyond distortion. As Europe entered the age of science, clocks became the heart of civilization. The ringing of church bells structured daily life. Later, the mechanical precision of pendulum clocks allowed sailors to cross oceans without losing their way, measuring longitude by comparing local time with the ticking of a trusted clock. The railroad age demanded even more rigor. To run trains safely across continents, cities adopted standardized time zones, binding millions of lives to the same shared rhythm. Time was no longer just a flow. It became an industry, a commodity, a force organizing entire societies. In all of these developments, the same assumption held sway. Time was absolute. Whether marked by shadows on stone, by pendulums swinging in cathedrals, or by steam trains rushing across iron tracks, people believed they were measuring something eternal and uniform. Then came a quiet revolution. In the late 19th century, experiments with light began to show cracks in this certainty. If Newton was correct, then the speed of light should shift, depending on the motion of the observer, just as the speed of an arrow changes depending on whether you run toward it or away. But experiment after experiment, culminating in the famous work of Michelson and Morley, showed otherwise. Light defied expectation. It sped past at the same pace, no matter how you moved. It was as if nature was hiding a secret, refusing to obey the old rules. Einstein, young and obscure, grasped the meaning. To preserve the constancy of light, something else had to give. Either space was not what we thought, or time was not what we thought, or perhaps both. The result was special relativity, a theory that shattered the Newtonian vision. Einstein showed that time and space are not separate arenas, but interwoven threads in a single fabric. Move fast enough, and time itself will slow for you, relative to others. Race near the speed of light, and the seconds you experience will not match the seconds of those left behind. This discovery was staggering. It meant that time was not universal. It meant that the rhythm of existence could differ for two travelers depending on their motion. The absolute stage imagined by Newton dissolved. Reality became relative, and time itself became negotiable. But Einstein did not stop there. If motion alone could bend the flow of time, then what of gravity, that most mysterious of forces? Was it possible that gravity too could twist the fabric of time? He turned the problem inside out. Instead of imagining gravity as an invisible pull between masses, Einstein reimagined it as the curvature of space-time. The Earth is not tugged by the sun across empty space. Rather, the sun bends space-time around it, and Earth simply follows the curved path of that geometry. In this picture, space-time is no longer passive. It is active, dynamic, shaped by matter and energy. And if time is woven into space-time, then wherever gravity curves the geometry, time itself must also bend. This is where the story begins to sound surreal. If the sun bends space, it also bends time. If a black hole bends space to the breaking point, it also slows time nearly to stillness. To stand deeper in a gravitational field is to live more slowly than someone higher up. The very river of time, once thought eternal and absolute, is dragged by gravity, like water in a whirlpool. And so we find ourselves at a precipice. The flow of time we once trusted has become an illusion. The clocks that keep our days are faithful within their own tiny realms, but across the cosmos, time itself is uneven, distorted by mass and motion. The stage of reality is not rigid, but pliable, not universal, but local, not absolute, but relative. As we move forward, we must confront this strangeness directly. To understand why gravity slows time, we must leave behind the comfort of Newton's steady ticking and enter the curved geometry of Einstein's spacetime. The idea that time could bend was once unthinkable. Yet as the 20th century unfolded, evidence began to mount that Einstein's vision was not just speculation, but reality itself revealed. Still, before diving into the proofs and experiments, it is worth pausing on the strangeness of the claim. What does it mean to say that time is flexible? What does it mean that gravity can slow its passage? Think of your own life as a line drawn across a great invisible fabric. This line is called your world line, and each step you take, each beat of your heart, marks a point upon it. In Newton's world, this line would be stretched across a flat stage, measured out by equal ticks of an absolute clock. But in Einstein's world, the fabric can bend, stretch, and ripple. Your world line is not fixed upon a flat grid. Instead, it curves through a living geometry shaped by matter and energy. The flow of seconds along that line can change depending on the path. Imagine two twins, one staying on Earth and the other venturing into deep space. If the traveling twin flies at speeds close to that of light and then returns, they will discover that fewer years have passed for them than for the twin left behind. This is not science fiction, but a direct consequence of relativity. Time is no longer something you merely live through. It becomes something that can be altered, stretched, or compressed. And if motion alone can do this, gravity can do even more. The Earth beneath your feet bends space-time. It is not dramatic compared to the pull of a neutron star or the crushing weight of a black hole, but it is real. The closer you are to Earth's center, the deeper you are in its gravitational well. That depth subtly slows your clock. Compared to someone standing on a mountaintop, the effect is tiny, measured in nanoseconds, but modern atomic clocks can detect it. Two clocks placed at different altitudes will tick out of step. Time itself is not universal, even across the span of a single planet. This realization forces us to change how we imagine reality. When you look at the stars, you are not only looking across space, but also across time, through intervals that may have been stretched by cosmic distances and distorted by gravitational fields. The universe is not a single synchronized stage, but a symphony in which each instrument plays at a slightly different tempo. The illusion of uniform time is sustained only by the limits of our senses. Our eyes and hearts are too coarse to notice the subtleties. Our lives are too brief to perceive the distortions. And yet the universe never lies. It whispers its truths in starlight, stretched by gravity, in the decay of particles racing through the atmosphere, in the necessity of correcting satellites that orbit above us. Our technology and experiments reveal what our intuition cannot. They reveal that time is as much a part of the cosmic fabric as space, and like space, it bends to gravity's hand. To take time for granted is natural. It feels so steady, so dependable, that we build our lives upon it without question. But the reality is deeper, stranger, and more unsettling. Time is not given equally everywhere. It is not an endless march detached from the world. It is tied to the geometry of space-time, and wherever gravity curves that geometry, time slows. This is where our journey must go next. To understand why gravity slows time, we must look more closely at what Newton once imagined and what Einstein replaced it with. We must move from a world of forces acting across empty void to a universe in which matter and energy shape the very arena of existence. Only then can we see how time, that most intimate companion of our lives, is pulled and stretched by the cosmos itself. In the beginning of the scientific age, the world seemed mechanical. Isaac Newton, working in the 17th century, looked at the apple falling from a tree and the moon circling the earth and declared that both were ruled by the same law. Gravity, he said, was a force, invisible, yet universal, pulling all masses together. It acted across distance with perfect precision, holding the cosmos in order as if the universe itself were a grand machine. To the thinkers of his time, this was revelation. At last there was a way to predict the dance of the heavens with the same certainty that one could predict the fall of a stone. Newton described his vision in a language of absolutes. Space was absolute, the stage upon which all motion played out. Time was absolute, flowing uniformly, without regard to anything within the universe. These absolutes were not just conveniences of thought. They were seen as fundamental realities. If the universe were a clock, then absolute space and time were its casing, eternal and unchanged. Within that casing, the gears of gravity turned, pulling planets, moons, and comets along their paths. The success of this picture was overwhelming. With Newton's laws, astronomers could forecast eclipses, sailors could navigate across oceans, and engineers could build machines that mirrored the clockwork of the heavens. The Newtonian cosmos was majestic and ordered, a universe whose laws could be written in mathematics so clear that they seemed to approach the divine. For centuries, no one doubted that gravity was a force transmitted instantly across the void, pulling on objects no matter how distant. Yet even as Newton's theory triumphed, it carried an unease. How could a force act across empty space with no medium, no thread, no mechanism? Newton himself admitted discomfort. He called it an absurdity that mass could attract mass at a distance without anything in between. But his equations worked, and in science, what works often stands until something better arrives. That something better would not come until centuries later, when Einstein reimagined gravity not as a force, but as the bending of space-time itself. To get there required dismantling Newton's absolutes. The first crack came not from gravity, but from light. Experiments showed that the speed of light refused to change, no matter how one moved toward or away from it. Newton's absolutes could not contain this strange constancy. Einstein took the step no one else dared. He declared that space and time themselves were not rigid stages, but parts of a single flexible fabric. Events do not unfold against an eternal backdrop. Instead, they occur within a geometry that can bend and shift. Motion distorts the flow of time and the measure of distance. Two observers moving differently will not agree on what is simultaneous. The absolutes Newton trusted dissolve into relativity. Once this was understood, gravity could no longer remain an invisible pull. Einstein's general relativity replaced Newton's force with curvature. Mass and energy tell space-time how to bend, and bent space-time tells matter how to move. The Earth orbits the Sun not because the Sun exerts a tug across 93 million miles, but because the Sun warps the geometry of space-time, and Earth's path is curved by that geometry. Gravity becomes geometry itself, and time becomes part of that geometry. This union of space and time is not a poetic metaphor. It is a mathematical truth tested by observation. A planet's orbit can be predicted more precisely by Einstein's equations than by Newton's. The bending of starlight by the sun, confirmed during an eclipse, revealed that space-time itself was curved. And most astonishing of all, Einstein's theory predicted that time would run differently depending on the depth of a gravitational field. The very rhythm of the universe was no longer universal. The journey from Newton to Einstein is more than a scientific advance. It is a shift in worldview as profound as any in human thought. Newton saw the universe as a machine running within a fixed stage. Einstein revealed the stage itself to be dynamic, responsive, alive. And within that living fabric lies the answer to why gravity slows time. To reach that answer, we must now enter the geometry itself. We must look at how space-time is stitched together, how world lines bend, and how the ticking of a clock is stretched by curvature. Only then will the mystery of gravitational time dilation come into full view. Newton's picture of the cosmos was so compelling that it reigned for centuries, not merely as a scientific framework, but as a philosophy of existence. The universe seemed mechanical, predictable, an eternal engine of cause and effect. Each planet circled in a precise ellipse. Each tide rose and fell as expected. Each pendulum swung in harmony with an unseen rhythm. Even when irregularities arose, as in the orbit of Mercury, with its slight but persistent drift, the temptation was always to explain them away within the Newtonian scheme. The belief in absolute space and absolute time was too powerful, too intuitive, to abandon easily. Yet questions persisted. If gravity was a force reaching across space, did it act instantaneously? Did the sun's pull reach Earth without delay, as Newton assumed? Or was there a finite time for its influence to travel? Newton could not answer, and the theory offered no explanation. This puzzle lingered in the background until light itself forced the issue. The discovery that light has a constant speed, regardless of the observer's motion, shook the foundations of physics. Imagine riding on a train moving swiftly down the track. If you throw a ball forward, someone standing beside the track will see the ball move faster than you do, because they add the train's speed to the ball's speed. Common sense says that light should behave the same way, but experiments proved that it does not. Whether the Earth is moving toward a star or away from it, the starlight arrives at exactly the same speed. It was as though the universe were conspiring to keep this one number sacred. The only way to resolve this contradiction was to alter the fabric of space and time themselves. Einstein did so by merging them into space-time, a four-dimensional continuum in which distances and durations are intertwined. Space and time lose their independence. Events that seem simultaneous to one observer may not be simultaneous to another. A journey through space is also a journey through time, and the measure of one cannot be separated from the measure of the other. From this insight arose the idea of world lines, the paths traced by objects as they move through space-time. A stone tossed into the air traces a curved world line before falling back into your hand. A planet circling a star traces a looping world line that stretches across centuries. And each world line has its own measure of proper time, the ticking experienced along that path. This is where the Newtonian vision unravels completely. There is no longer one universal time against which all things can be measured. There are many times, each belonging to its own path through the fabric. Einstein then turned to gravity, the deepest mystery of them all. If space-time is a fabric, then mass and energy can stretch and bend it. Imagine a heavy sphere resting on a rubber sheet. The sheet curves beneath its weight, and smaller spheres placed nearby roll inward along the curves. They are not pulled by a hidden thread. They are simply following the shape of the surface. So too does Earth follow the curve of space-time around the Sunday. There is no mysterious force leaping across empty space. There is only geometry, telling matter where to move. This idea does more than explain motion. It explains time itself. If time is bound up with space, then when space-time bends, time must bend with it. A clock carried close to a massive object will tick more slowly than one far away. Not because the mechanism is faulty, not because anything interferes with its gears or oscillations, but because the very fabric through which it moves is stretched. Gravity slows time because gravity is the curvature of space-time, and time is woven into that curvature. The elegance of this picture is breathtaking. Instead of a universe governed by invisible pulls across distance, we have a cosmos whose structure is itself dynamic. Matter shapes space-time, space-time shapes motion, and time is no longer absolute but relative to position and path. What Newton saw as absolutes are revealed as illusions, and yet, Einstein's revolution was not accepted instantly. Many scientists were skeptical, some openly hostile. The mathematics was difficult, the implications disturbing. To suggest that time itself could be slowed or stretched sounded absurd, but the theory made predictions, precise and testable. And in science, predictions are the currency of truth. One of the earliest came in 1919, when astronomers set out to observe a solar eclipse. If Einstein was correct, the sun's mass would bend the path of starlight passing near it, shifting the apparent positions of stars. The eclipse provided a chance to see them against the darkened sky. The results matched Einstein's equations. Starlight bent exactly as predicted. The world awoke to headlines proclaiming a new universe. Still, the most profound consequence was not the bending of light, but the bending of time. For the first time in history, humanity was forced to accept that the flow of time was not universal. It depended on motion. It depended on gravity. It depended on where you stood in the great fabric of existence. This was the step beyond Newton. The old vision of a mechanical cosmos running within the fixed casing of absolute time gave way to a living space-time, shaped by matter and shaping it in return. It was a vision more flexible, more beautiful, and far more unsettling. The confirmation of Einstein's vision was like a curtain lifting on a stage we had always occupied but never seen. To imagine gravity as geometry is not easy, for our senses were shaped to navigate the surface of Earth, not the vastness of space-time. Yet with patience, the idea reveals its clarity. The Earth does not feel a tug from the Sunday, it follows a curve written into space-time itself. Astronauts orbiting Earth do not float because gravity disappears, but because they too follow curved paths, falling forever along the bent fabric. Gravity is not a chain pulling them downward. It is the geometry through which they move. This change in perspective is not just a refinement of Newton's law. It is a complete rewriting of the meaning of reality. In Newton's cosmos, time was separate from space. In Einstein's, they are inseparable. In Newton's, forces acted across emptiness. In Einstein's, emptiness is not empty at all, but a fabric shaped by energy. In Newton's, clocks ticked in unison throughout the universe. In Einstein's, clocks disagree, each tracing its own tempo along its path through space-time. The most startling implication is that gravity must slow time. Consider a light beam climbing away from the surface of Earth. To an observer at the top of a tower, the light will appear redder than it was at the bottom. Its waves stretched as though time itself had slowed in the depths of Earth's gravity. This is not illusion, but inevitability, a direct consequence of space-time curvature. If light must lose energy to climb out of a gravitational well, and if the speed of light cannot change, then its frequency must shift. And since frequency is simply the ticking of light's oscillations, what has slowed is time itself at the lower altitude. Einstein predicted such effects with unflinching confidence. He believed that gravity and acceleration were equivalent, that standing on Earth was indistinguishable from standing inside a rocket, accelerating upward. If acceleration could slow clocks, then so could gravity. The mathematics confirmed it, and soon experiments would too. But even before the measurements, the logic was undeniable. If space-time is geometry, and if time is a coordinate within that geometry, then wherever geometry curves, time must warp. This is why Newton's universe had to be abandoned. Its absolutes could not bend, could not yield, could not explain why light refused to change speed, or why starlight bent around the Sunday. Only Einstein's fabric, pliable and dynamic, could make sense of these mysteries. With that fabric came the recognition that time is not impartial. It can run faster or slower depending on the depth of gravity's embrace. From this realization flows a cascade of wonders. It means that two people standing at different altitudes live at slightly different rates. It means that a satellite orbiting Earth must correct its clocks to stay synchronized with the ones on the ground. It means that in the crushing grip of a black hole, time for an infalling traveler stretches toward eternity as seen by distant eyes. Gravity does not simply hold us to the Earth. It molds the very pace of existence. The journey from Newton's force to Einstein's spacetime is one of the greatest intellectual leaps in human history. It is the passage from a cosmos that behaves like a machine to one that behaves like a living fabric. It is the recognition that time is not the same for all, that the universe has no single clock, that reality is richer and stranger than intuition allows. And this is where our path now leads. To understand in detail why gravity slows time, we must leave behind metaphors and step directly into geometry. We must see how space-time is stitched, how the shapes of world lines dictate the ticking of clocks, and how gravity stretches those intervals. The next step in our journey is to explore the geometry of time itself, to trace how Einstein's equations give birth to the slowing of moments in the presence of mass and energy. To see why gravity slows time, we must step into the language of geometry, for geometry is the heart of Einstein's vision. When we imagine space, we picture length, width, and height, the three dimensions that describe every position. But Einstein showed that there is a fourth woven into them, inseparable from the rest. That fourth is time. Together, they form space-time, not a passive container, but an active fabric whose structure is determined by matter and energy. Picture a traveler carrying a perfect clock. Each tick of that clock is a marker of what physicists call proper time, the time experienced along that traveler's path through space-time. The clock does not measure some universal rhythm. It measures the length of the traveler's journey through the fabric, much as a piece of string measures the length of a curve drawn on paper. Two travelers taking different routes between the same events can record different amounts of proper time, just as two paths drawn across a map can have different lengths. This is a hard concept to absorb because human intuition tells us that time is independent of path. If you and I part ways and meet again tomorrow, our instincts insist that exactly one day has passed for both of us. Yet relativity shows that this is not always so. If one of us travels swiftly or passes near a massive body while the other remains behind, we will not agree when we reunite. Our clocks, both perfect, both faithful, will reveal different totals of proper time. To grasp this, think of space-time as a landscape. A straight road across a flat plane represents motion without gravity, smooth and uniform. In this case, two travelers moving steadily and returning together might agree on the passage of time, but introduce hills and valleys to the landscape, and the paths change. A traveler who dips into a valley must climb out again, lengthening the route. Likewise, in space-time, a traveler who dips into a gravitational well traces a different curve, one where the intervals of time are stretched. Clocks reveal this stretching in ways light cannot disguise. A clock deep in a gravitational field will tick more slowly than one high above. The geometry itself demands it. Proper time is measured along the path of the clock through space-time, and in curved regions, that path yields fewer ticks compared to a similar path in flatter regions. This is not a matter of the clock running poorly. The mechanism, whether pendulum, quartz, or atom, is flawless. What changes is the geometry through which the clock moves, and geometry dictates rhythm. Even the speed of light, so constant in every other way, bows to this geometry. A beam climbing from the surface of Earth to a higher altitude is stretched, its frequency reduced, as though its oscillations had slowed, but they have not slowed in any local sense. To the light itself, nothing has changed. The slowing is revealed only when compared across different depths of gravity, This comparison uncovers the truth. Space-time is not uniform, and time itself is part of that uneven terrain. The mathematics of general relativity gives this landscape precise form. It shows that mass and energy determine the curvature, and that curvature shapes world lines, the tracks along which both matter and light must travel. In Newton's vision, forces drew objects along. In Einstein's, geometry is the guide. To exist is to move through space-time, and to move through space-time is to experience proper time. Where geometry curves, proper time bends with it. This union of geometry and time is perhaps the most profound insight of modern physics. It means that time is not a universal drumbeat outside the world, but an element within it, as mutable as space, as responsive as light. To understand why gravity slows time is to understand that time is stitched into the same fabric that bends beneath planets and stars. And so we arrive at a startling conclusion. The question is not why gravity should affect time, but how could it not? If time is part of space-time, and if gravity is the curvature of space-time, then the slowing of time is not an anomaly, but an inevitability. It is the geometry itself announcing its presence, inscribed in every tick of a clock, every wave of light, every heartbeat that passes beneath the pull of a star. The stage is now set to see these effects not as abstractions, but as predictions. For Einstein's theory did more than imagine geometry. It foretold measurable consequences, ways in which the bending of time would reveal itself to experiment. These predictions would become the proof that time is not absolute but curved, stretched, and slowed by the gravity of the cosmos. Time as geometry is a notion that challenges the very core of how we see reality. Our senses were never meant to perceive it directly. When you look at a mountain, you see a shape of stone and snow, not the invisible geometry that bends the path of light around it and slows the ticking of clocks upon its slopes. Yet that geometry is there, silent and unyielding. Space-time curves, and all who move within it follow its contours, whether they know it or not. Imagine a sheet of fabric stretched taut. If you draw two lines straight across it, their length is simple to measure. Now press your hand into the sheet, bending it downward into a depression. End 1. End. Draw those same lines again. One line may dip into the depression, stretching longer, while another skims the edge. The sheet is the same. The lines are both straight within the surface, yet the lengths differ because of the curvature introduced. Space-time behaves in this way, though far more subtly, and time is as much a part of that surface as space. Proper time, the time measured along a world line, is the most faithful expression of this truth. It cannot be cheated or ignored. A clock that follows a path through curved space-time reveals that the total number of ticks depends on the geometry of that path. The effect is small in everyday life, almost imperceptible. But in the grand scales of the universe, or in the crushing grip of compact stars, it becomes decisive. It is as if the cosmos itself is sculpted in such a way that every traveler carries their own personal rhythm, unique to their journey. To picture this, consider two explorers starting at the same point on Earth. One climbs a mountain, the other remains in the valley. Both carry identical atomic clocks, each capable of keeping time to an accuracy of billionths of a second. After a day, they meet again and compare their clocks. The one in the valley, deeper in Earth's gravity, will have ticked fewer seconds than the one on the mountain. The difference is tiny, but real, proof that gravity curves time even across such a modest height. What the explorers witness is not a malfunction, but a glimpse of geometry in action. The same principle applies on cosmic scales. Near a neutron star, where a mass greater than that of the Sun is squeezed into a sphere only tens of kilometers across, the curvature of space-time is extreme. Clocks there would tick so slowly compared to those far away that a single hour on the surface might correspond to many hours in open space. If one twin lived near such a star while the other remained distant, their reunion would reveal not only differing experiences, but differing totals of life lived. Gravity itself would have rationed their time unequally. These distortions are not confined to matter. Light too follows the geometry, bending as it passes near massive bodies. But the bending of light is only half the story. The stretching of time is the other half, and it is more subtle. When light climbs away from a massive object, its frequency is redshifted, its oscillations stretched. This redshift is not because the light has slowed, for the speed of light is always the same. It is because time itself flows differently at different points in the gravitational field. This interplay of light, clocks, and geometry forms the essence of Einstein's prediction. The fabric of space-time dictates the pace of all motion, whether of particles, photons, or human lives. Gravity is no longer a mysterious force pulling on masses. It is the shape of the arena itself, and time is woven into that shape. To ask why gravity slows time is to ask why rivers follow the curves of their valleys. They do so because the landscape demands it. The beauty of this realization lies in its inevitability. Once you accept that space and time are fused into space-time, and that gravity is the bending of that space-time, the slowing of time follows naturally. There is no escape from it, no way to wish it away. Time cannot remain rigid while its partner space bends. They are joined, and what happens to one happens to the other. As profound as this insight is, it would remain an elegant abstraction without proof. But Einstein's genius was not only to imagine the geometry of time, but to foresee its consequences. He predicted specific, testable effects that would reveal the stretching of time under gravity's hand. The next step in our journey is to see how these predictions unfolded, how thought experiments with elevators and beams of light gave way to experiments on Earth and beyond. The strangeness of time as geometry becomes clearer when we consider the principle of equivalence, one of Einstein's most daring insights. He realized that being at rest on Earth, feeling the downward pull of gravity, is indistinguishable from standing inside a rocket, accelerating upward in empty space. The pressure of the floor against your feet feels the same in both cases. If you drop an object in the rocket, it will fall just as it does on Earth. This equivalence between acceleration and gravity was not a metaphor, but a fundamental clue. Imagine that rocket drifting in deep space, far from any stars or planets. If it fires its engines, accelerating steadily, light shining across the cabin will appear to curve downward, as though pulled by a force. A clock near the floor will tick more slowly than a clock near the ceiling. Now replace the rocket with a building on Earth. The bending of light and the slowing of clocks are the same. Gravity and acceleration are not merely similar. They are two expressions of one underlying truth. From this principle flows the inevitability of gravitational time dilation. If acceleration stretches the rhythm of time, so too must gravity. The geometry of space-time demands it. The equations Einstein wrote give precise form to this prediction, describing how time ticks more slowly the deeper one goes into a gravitational field. This is not just an abstract curiosity. It is measurable, real, and essential to the way the universe works. Clocks are our guides into this hidden world. They are not only tools of convenience, but instruments that reveal the structure of space-time itself. The more precise our clocks, the more clearly they expose the bending of time. In the early 20th century, such measurements were out of reach. But Einstein trusted his reasoning, and his predictions would soon find support in experiments that tested light, matter, and the very flow of time. The path to these experiments begins with thought. Consider an elevator rising through space, accelerating at a steady rate. A beam of light enters through a side window. To someone inside, the elevator moves upward, while the beam continues straight. Yet, because the floor rises during the beam's travel, the light appears to curve downward, as if deflected by a gravitational field. This thought experiment shows that light must bend in gravity's presence. When astronomers confirmed the bending of starlight near the Sun, they confirmed not only the curvature of space, but the curvature of time as well. The geometry of time reveals itself in still subtler ways. Take two identical clocks, one placed at the bottom of a tall building and another at the top. According to Einstein's equations, the clock at the bottom will tick more slowly, for it is deeper in Earth's gravitational field. Though the difference is minuscule, it is inexorable, a feature of the geometry itself. Modern atomic clocks, with precision unimaginable a century ago, now measure this difference with ease. What was once a prediction is now an everyday truth of physics. This recognition reshapes how we see the cosmos. Time is not the same everywhere. It depends on where you stand in the geometry of space-time. High on a mountain, time flows a little faster than at sea level. Near a star, slower still. At the edge of a black hole, nearly to a halt. The universe is not synchronized by a single clock, but fractured into countless rhythms, each dictated by the curvature of space-time. And yet, despite this strangeness, the geometry of time is not chaos. It is governed by precise laws, equations that allow us to predict exactly how time will bend in any gravitational field. Einstein's general relativity is a map of this landscape, and with it, we can navigate from Earth to the stars. We began with Newton, who saw gravity as a force acting across a stage of absolute time. We now stand with Einstein, who showed that gravity is the bending of space-time, and that time itself is part of the fabric that bends. The illusion of absolute time is gone, replaced by a deeper truth. Gravity slows time because time is geometry, and geometry is curved by mass and energy. From here, our journey turns to Einstein's predictions in detail. He foresaw not only the bending of starlight, but the slowing of clocks, the redshifting of light, and the freezing of time near horizons. These predictions would soon be tested, first by thought, then by experiment, until the flexible nature of time became undeniable. Einstein's vision of curved space-time was not a theory left to linger in abstraction. It was a daring declaration that the universe itself behaves in ways no human had ever experienced. And from this vision flowed predictions as strange as they were precise. If gravity is geometry, then time must slow in the presence of mass. If acceleration and gravity are equivalent, then clocks in different places must disagree. If light must always race at the same speed, then its color and rhythm must stretch as it climbs out of a gravitational well. These predictions were not guesswork. They were the logical outcome of Einstein's equations, carved from the principle that the speed of light is constant and that geometry governs motion. Each prediction carried consequences that could, at least in principle, be measured. Each dared nature to prove Einstein wrong. The first of these was the gravitational redshift. Imagine a photon born at the surface of the sunday. To escape the sun's gravity, it must climb upward through curved space-time. Yet light cannot lose speed, for the speed of light is fixed. Instead, it loses energy, and the only way to lose energy, while maintaining speed, is to stretch its wavelength. To observers far away, the photon appears redder, shifted to longer wavelengths. This stretching is not a trick of perception, but a fundamental sign that time itself flows differently at the sun's surface than in the emptiness between stars. Einstein also predicted that clocks deeper in a gravitational well would tick more slowly than clocks higher up. The principle of equivalence makes this unavoidable. In an accelerating rocket, a clock near the floor experiences a stronger effective gravity than one near the ceiling. Signals between them arrive slightly shifted, revealing that time itself runs differently at different heights. Replace the rocket with a planet, and the conclusion is the same. On Earth, a clock in a basement will run more slowly than a clock on a rooftop. The difference is minuscule but real, a whisper of the geometry of time. Another prediction arose from Einstein's thought experiments with elevators. Consider again the light beam crossing a room. In an accelerating frame, the beam curves downward, revealing that acceleration bends the path of light. By equivalence, gravity must bend light as well. Thus, starlight grazing the edge of the sun should shift in position, deflected by the sun's curved space-time. Newton's theory had offered no such prediction, but Einstein's demanded it. Even more dramatic was the prediction that near an extremely dense object, such as a black hole, time would stretch toward infinity. To a distant observer, the ticking of a clock falling toward the horizon would slow and then freeze. The light escaping from that region would be stretched endlessly, fading into darkness. This was not yet confirmed in Einstein's lifetime, but it followed directly from his equations. These predictions form the backbone of general relativity. Each is not a single claim, but a suite of consequences, each testable in its own way. If one failed, the whole edifice would collapse. But if they held, then the universe itself would reveal that gravity does not merely shape motion, but shapes time. For Einstein, these were not matters of speculation, but matters of necessity. Once you accept that space-time is curved, once you see that time is part of that curvature, then redshifts, time dilation, and the slowing of clocks are unavoidable. They are written into the very fabric of the equations. To deny them would be to deny the geometry itself. As the years passed, experiments would rise to meet these predictions. From the shifting of spectral lines in starlight, to the slowing of clocks in towers and valleys, to the deflection of light around the sun, the evidence would grow. But in these early years, the predictions themselves were bold enough to shake the foundations of thought. Humanity was no longer bound to a universal time. It was bound to a flexible one, bent by mass and energy, shaped by the same force that holds our feet to the ground and guides the planets around the Sunday. Einstein had transformed gravity from a mysterious pull to a sculptor of space-time. And with that transformation came the revelation that time, our most intimate companion, is not what it seems. It is relative, mutable, and bound to the same geometry that curves the paths of stars. Einstein's predictions did not remain locked in the realm of imagination. They were too precise, too bold, too demanding to be left untested. The redshift of light, the slowing of clocks in gravity, the bending of starlight, these were not vague speculations, but hard consequences of the geometry of space-time. Each would eventually be put to trial. But even before the experiments, Einstein used simple reasoning to make their reality vivid. His thought experiments were lanterns carried into the dark, illuminating truths before instruments could catch up. Take the case of the elevator, a box sealed against the outside world. If it accelerates upward in empty space, a beam of light sent across from one wall to another will appear to curve downward, striking the opposite wall lower than expected. The acceleration of the elevator floor mimics gravity. The principle of equivalence declares that these two situations, acceleration and gravitation, are the same in every way. So if light curves in the accelerating elevator, it must also curve in a gravitational field. What seems a playful exercise in imagination becomes a profound statement about the universe. From this reasoning, Einstein declared that starlight grazing the sun must bend. The angle was calculable, precise, and distinct from what Newtonian mechanics would predict. When astronomers measured it during the eclipse of 1919, they confirmed Einstein's claim. Headlines proclaimed that Newton had fallen, and a new universe had risen in its place. The bending of starlight was the first public triumph of general relativity. But for Einstein, it was only one piece of the puzzle. The redshift of light was another. Consider two identical clocks, one on the ground floor of a building, the other on the top floor. A pulse of light sent upward from the lower clock must climb through gravity to reach the higher one. As it climbs, its wavelength stretches. The higher clock interprets this stretch signal as ticking more slowly than its own rhythm. Thus, the lower clock runs slow compared to the higher one. The geometry of space-time demands it, and the redshift of light reveals it. Einstein also foresaw that in regions of stronger gravity, such as near massive stars, the effect would be magnified. Spectral lines in the light from such stars would be shifted toward the red compared to those from less massive ones. Astronomers searching the skies would one day see this shift and confirm that time itself ran differently on stellar surfaces. Perhaps the most dramatic of Einstein's predictions was the behavior of time near extreme gravitational fields. In his equations lay the seeds of what we now call black holes. Near their horizons, time for a distant observer slows, almost to a standstill. A clock falling inward ticks ever more slowly, its signals stretched until they fade away. To the falling clock itself, nothing seems strange. Its ticks remain steady, its moments flow as always. But to those watching from afar, it appears trapped, frozen on the brink of eternity. This was not mere fantasy, but a consequence of geometry carried to its limits. What made these predictions extraordinary was not their strangeness, but their necessity. They were not choices Einstein inserted at will. They were the unavoidable outcome of the equations. Once you accept that space-time is curved, if space-time bends, then light must bend, clocks must disagree, and time itself must slow under gravity's hand. Einstein often spoke of his confidence in these predictions. He trusted the elegance of the mathematics, the consistency of the reasoning, the way every piece fit together like parts of a vast cosmic puzzle. He believed that experiments, when they came, would confirm what the equations already whispered, and history proved him right. But before the instruments caught up, the thought experiments were enough to reveal the new world. They showed that time is not universal. They showed that gravity is not a force pulling through void, but geometry itself. They showed that our daily sense of time as absolute and unyielding is an illusion born of limited experience. The stage was prepared for experiments that would, in time, measure these effects directly. Einstein had drawn the map. It was now up to science to follow it into the strange and beautiful landscape of a universe where gravity bends not only space but also time. Einstein's predictions might have remained a majestic theory, admired for its elegance but doubted for its practicality, had not experiments risen to meet them. The bending of starlight during the eclipse of 1919 made headlines, but even that spectacular confirmation was only the beginning. The true test of general relativity would be whether the subtle slowing of time itself could be detected, not in the heavens alone, but here, on Earth. For decades, technology lagged behind the demands of Einstein's equations. To measure the difference in clock rates between a rooftop and a basement requires instruments of extraordinary precision. Pendulums and gears could never reveal such subtleties. Even the most careful mechanical devices were blind to the billionth of a second differences predicted by relativity. Yet human ingenuity, relentless in its pursuit of measurement, closed the gap. By the mid-20th century, atomic clocks were born, their rhythm set not by swinging pendulums or vibrating crystals, but by the steady oscillations of atoms themselves. Each tick was the whisper of nature's most fundamental transitions, as reliable as the universe could offer. Armed with these clocks, scientists could at last confront Einstein's claim that gravity slows time. The Pound-Rebka experiment of 1959 provided the first decisive proof. In a tower at Harvard University, gamma rays were emitted from the bottom and detected at the top. According to relativity, the rays should shift in frequency as they climbed, their oscillations stretched by the difference in gravitational potential. The shift was unimaginably small, but the apparatus was ingenious, using the Mössbauer effect to detect the change with exquisite sensitivity. The results matched Einstein's prediction. Time truly ran more slowly at the bottom of the tower than at the top. The implications were staggering. The effect that seemed too subtle for human experience, the mere whisper of gravity upon the flow of moments, was now revealed as a measurable truth. It was not philosophy. It was not speculation. It was physics, confirmed by experiment. From that day forward, the slowing of time in gravity was no longer an abstract idea, but an observed feature of reality. In the years that followed, atomic clocks grew ever more precise. Scientists carried them aboard airplanes, comparing their ticks to clocks left on the ground. As predicted, those flown at higher altitudes and lower gravity ran faster, while those moving swiftly experienced time dilation from motion as well. Every test confirmed Einstein's vision. The universe does not share a single heartbeat. It offers many, each unique to position and motion, each written into the geometry of space-time. These conformations reshaped not only science but technology. The satellites that make up the global positioning system orbit high above Earth, where gravity's pull is weaker and time runs faster than on the surface. Without correcting for this difference, the system would accumulate errors of kilometers each day, rendering it useless for navigation. Einstein's equations, once thought the height of abstraction, now guide aircraft, ships, and even the smartphones in our pockets. Our daily lives depend on the fact that gravity slows time. From Einstein's thought experiments to towers in Harvard, from airplanes carrying clocks to satellites guiding travelers, the story is one of prediction made real. The bending of time by gravity is no longer a mystery hidden in mathematics. It is a truth woven into the operation of the modern world, and yet the experiments on Earth and in orbit are only glimpses of the greater extremes awaiting in the cosmos. Black holes, neutron stars, galaxies themselves. These are arenas where the slowing of time becomes not subtle but profound, where the geometry of space-time grips moments so fiercely that the very concept of simultaneity begins to break apart. But before we journey outward to those extremes, we must pause to recognize the triumph here at home. Einstein predicted that gravity slows time. Experiments proved him right. Technology now relies on that truth. The flow of time we once believed absolute has been revealed as relative, bent by mass and energy, shaped by the same force that binds the Earth to the Sunday. Einstein's predictions have become the foundation of our understanding of reality. They have shown us that time is not a background against which events unfold, but an active participant in the cosmos, curved and stretched by the geometry of space-time. The stage is now set to see how this plays out on our own planet, where mountains and valleys, oceans and satellites reveal the slowing of time, not in theory, but in the very heartbeat of Earth itself. Einstein's predictions were bold, and the experiments of the mid-20th century had begun to confirm them. But what remained even more astonishing was that the slowing of time by gravity was not only a feature of distant stars or exotic black holes. It was happening here, on Earth, beneath our very feet. Time on Earth itself is not uniform. It is stretched and slowed by the gravity that holds us to the ground, and though the differences are subtle, they are real enough to be measured, tested, and used in the technology that guides our lives. The Pound-Rebka experiment of 1959 was the first great demonstration. From the top to the bottom of a building only a few stories tall, gamma rays revealed the slight stretching of time predicted by Einstein. It was a triumph of both theory and ingenuity, but it was only the beginning. The experiment showed that even across a height of just 22.5 meters, gravity bent the rhythm of time. A clock at the bottom of the tower ticked more slowly than one at the top. The difference was tiny, but it was enough to prove that the geometry of space-time was not confined to cosmic scales. It was here on Earth, whispering through every tick of every clock. As atomic clocks improved, scientists carried them to mountaintops and valleys, testing Einstein's prediction with ever greater precision. The results were always the same. Clocks at higher altitudes, where Earth's gravitational pull is slightly weaker, tick faster than those at sea level. At first, the difference seemed absurdly small, a few billionths of a second per day. But atomic clocks do not tire or waver. They reveal the truth without compromise. And the truth is that no two places on Earth share exactly the same time. This realization is almost unbearable to intuition. We are accustomed to thinking of time zones and calendars as conventions, human creations layered upon the unchanging flow of time. But relativity shows that time zones are not merely social agreements. They are approximations of a deeper fact. Time itself is local, tied to gravity, tied to geometry. The clock on a mountain and the clock in a valley do not agree because they cannot. The fabric of space-time does not permit them to share the same rhythm. These effects might have remained curiosities, the domain of laboratories and physicists, had it not been for a revolution in technology. When satellites were launched into orbit around Earth, carrying atomic clocks to guide navigation, engineers discovered that relativity could not be ignored. High above the ground, in weaker gravity, the satellite clocks ticked faster than those on Earth. At the same time, their rapid motion caused a slowing relative to the surface. Both effects, gravitational dilation and motion dilation, had to be accounted for, or the system would fail. The global positioning system, now relied upon by billions of people every day, would lose accuracy by kilometers within a matter of hours. The only way to make GPS work is to correct every clock for relativity, for both gravity and motion. In every car, every phone, every aircraft guided by GPS, Einstein's equations are at work, silently ensuring that the system holds together. Thus, relativity is not an abstraction confined to the blackboards of theorists. It is stitched into the infrastructure of modern life. The slowing of time by gravity is not a philosophical curiosity. It is a fact we depend on every day to navigate our world. And yet, the effects are not uniform. Earth itself is not a perfect sphere, and its gravity varies from place to place. Clocks at the equator tick slightly differently than clocks near the poles, for Earth's rotation flattens it into an oblate spheroid, changing the depth of the gravitational well. Even the mass of mountains and valleys contributes to subtle shifts in time, though they are tiny compared to the effect of altitude. The result is a planet where time itself is not evenly distributed, where the geometry of space-time inscribes differences into every point on the globe. To grasp this is to see Earth anew. It is no longer just a sphere of rock and water circling the Sunday. It is a stage of curved space-time, where gravity sculpts not only the paths of rivers and winds, but also the flow of moments. Our lives are lived not upon an absolute clock, but upon a world where time itself bends with the terrain. The recognition of this truth is one of the most humbling achievements of science. It means that when we look at a clock, we are not seeing the universal flow of time. We are seeing a local rhythm, shaped by Earth's gravity and position in space-time. And if gravity can bend time here, it can bend it anywhere, across the vast expanse of the cosmos. The slowing of time on Earth is the most immediate proof of Einstein's vision, a reminder that relativity is not remote, but intimate. It touches every moment of our lives, whether we notice it or not. From mountains to satellites, from valleys to laboratories, time is stretched and curved by the pull of Earth itself. And yet, as profound as these effects are, they are only a glimpse of what lies beyond. For if Earth's gravity can bend time by billionths of a second, then what happens near the densest objects in the universe? What happens when the fabric of space-time is pulled almost to breaking? To answer this, we must journey outward, to the realm of black holes, where time itself slows nearly to stillness. The discovery that gravity slows time was not merely a matter of theory, or even of a single decisive experiment. It became a story of repetition, refinement, and growing precision, each new measurement carving the truth deeper into the stone of science. After the Pound-Rebka experiment, physicists sought to test Einstein's prediction in more ways, and as atomic clocks grew more exact, the universe revealed its secrets with ever greater clarity. In the 1970s, scientists carried atomic clocks aboard jet airplanes, flying them around the world, while comparing them to identical clocks left on the ground. The results were a perfect harmony of relativity. The flying clocks ticked differently, slowed by their motion, yet also quickened by their higher altitude. Both special relativity and general relativity played their part. And when combined, the differences matched Einstein's equations exactly. What once seemed outlandish had now become routine. Time itself is flexible, and human beings had measured it in the span of a single flight. Later experiments carried atomic clocks into space, aboard satellites and missions circling the Earth. The results were the same. Clocks in orbit, farther from Earth's gravity, ran faster than their counterparts on the ground. These measurements confirmed that Einstein's predictions were not confined to laboratories or towers. They applied everywhere, from the surface of the Earth to the edge of the sky. The geometry of space-time does not compromise. Wherever there is gravity, time bends. The global positioning system made this fact impossible to ignore. Satellites orbit Earth at an altitude of about 20,000 kilometers, and their clocks tick faster by about 45 microseconds each day due to weaker gravity. At the same time, their rapid motion slows them by about 7 microseconds. The net effect is a gain of about 38 microseconds per day compared to clocks on Earth. That may seem negligible, but left uncorrected, it would create navigational errors of several kilometers within hours. To function at all, GPS must incorporate relativity into its very design. Einstein's equations are as essential to navigation as the satellites themselves. This is perhaps the most humbling twist of all. A theory born from thought experiments with elevators and beams of light has become the quiet foundation of modern life. Every time a driver follows a map on a phone, every time a pilot guides a plane across the sky, every time a ship sails safely into harbor, it is Einstein's relativity that keeps them on course. The slowing of time by gravity is not only a truth of physics, it is a tool of civilization. But the story does not end with satellites and clocks. Even here on Earth, the bending of time can be measured with such precision that it reveals differences in altitude of mere centimeters. Modern atomic clocks are so sensitive that lifting one by the height of a human hand is enough to change its ticking. In laboratories, scientists use this effect to map gravitational variations across landscapes. Time itself has become a tool for surveying Earth, as though the fabric of space-time were whispering the shape of the planet through the ticks of its clocks. These measurements reveal a deeper truth. Time is not an independent backdrop against which the drama of life unfolds. It is part of the stage itself, molded by the same forces that carve valleys and raise mountains. Just as rivers follow the contours of Earth, our lives follow the contours of space-time, each heartbeat and breath paced by the geometry in which it occurs. The notion of a single universal time was a comforting illusion. The reality is richer and stranger, countless local times, each tied to its place in the cosmos. And still, these earthly demonstrations are only shadows of what lies beyond. On Earth, the differences amount to nanoseconds, subtle but measurable. But near collapsed stars, or in the grip of a black hole, the effect becomes overwhelming. There, time does not merely slow, it verges on halting altogether, stretching seconds into eternities. Yet before venturing to those extremes, it is worth pausing on the wonder that we can detect relativity at all in our everyday environment. For billions of years, humans lived and died without suspecting that gravity bent time. To their senses, the flow of days was steady and universal. Only with the advent of atomic clocks and satellites did the veil lift, revealing a deeper truth. Now, with every use of GPS, with every laboratory experiment, humanity bears witness to the malleability of time itself. The Earth, then, is not merely a home. It is a proving ground for the strangest truths of the universe. It shows us that time bends here, in our cities and mountains, in our valleys and skies, and it prepares us for the greater revelations that await in the cosmos, where gravity does not whisper its power, but shouts it into the silence of space. Time on Earth is not uniform, though it feels that way to our senses. The rhythm of a heartbeat in a valley and the rhythm of a heartbeat atop a mountain are not quite the same. The differences are measured in billionths of a second, but those billionths accumulate. A person who spends their life in a deep gravitational well lives a little less, in terms of proper time, than one who spends it higher up. The difference is so small that no one would notice without the aid of the most sensitive instruments, but the principle is unshakable. Gravity stretches the fabric of space-time, and in doing so, it slows the ticking of every clock it touches, whether it is a machine or the beating of a heart. This idea unsettles our intuition, because human beings rely on shared rhythms. We arrange meetings, tell stories, remember histories, and dream of futures as though time were a single current carrying us together. Relativity reveals that beneath this shared illusion lies a fractured reality. Each of us carries our own clock, and that clock does not always agree with others. At the surface, our differences are invisible, so we live as if they do not exist. But the geometry of space-time records them without fail. No two paths through gravity are ever identical, and so no two flows of time are ever perfectly the same. Modern science has made this truth impossible to ignore. In laboratories, atomic clocks detect differences in elevation of mere centimeters. Raise a clock onto a shelf, and it will tick faster than one left on the floor. This ability to measure the bending of time so precisely has given rise to new forms of science. Geodesists, those who study the shape of Earth, now use clocks as instruments to map gravity itself. By comparing ticks between locations, they can detect variations in Earth's gravitational field caused by mountains, valleys, or even underground structures. Time has become a probe, a way to see the invisible hand of gravity sculpting the planet. The wonder of this achievement cannot be overstated. For thousands of years, humanity thought of time as divine, eternal, absolute. Then Newton taught us to see it as a universal backdrop, steady and impartial. Now we know it is local, pliable, responsive to the weight of the world beneath our feet. A truth once hidden in the fabric of reality is now revealed in laboratories, airplanes, and satellites, written into the everyday technology we depend upon. It changes the way we see ourselves. To live is to move through space-time, and to move through space-time is to experience time's flow along a particular path. That flow is shaped by Earth's mass, by its rotation, by its very shape. We are creatures of curved space-time, bound not only by gravity's pull, but by its slow reshaping of our lives at the smallest scales. Time is not a universal gift, but a local measure, portioned differently depending on where we stand. And yet, while these truths astonish us, they are only a prelude to the greater extremes that lie beyond. On Earth, gravity slows time by fractions of a second over a lifetime. Near collapsed stars or in the grip of black holes, the effect becomes overwhelming. There, the difference is not billionths of a second, but years, centuries, or eternity itself, depending on where one stands. The experiments with towers, airplanes, and satellites remind us that relativity is not remote. It is intimate, woven into the ordinary flow of our lives. But they also serve as stepping stones, guiding us toward the more dramatic arenas of the cosmos, where time does not merely whisper, but roars. The Earth shows us the principle. The stars will show us its power. And so our journey continues, moving from the familiar to the extraordinary. We leave behind the quiet distortions of time measured in laboratories and ascend into the heart of cosmic gravity wells, where time itself slows to a crawl and the geometry of space-time reveals its most awe-inspiring form. If Earth shows us the gentle hand of gravity slowing time, then black holes reveal its iron fist. Here, the bending of space-time is so extreme that it pushes relativity to its limits, taking what is subtle on our planet and magnifying it into a cosmic spectacle. To approach a black hole is to approach the edge of time itself, a place where moments stretch into eternities and the very meaning of past and future begins to blur. The story begins with the simplest solution to Einstein's equations, discovered not long after he published them. Karl Schwarzschild, working during the First World War, found a geometry that described the space-time around a perfectly spherical mass. His result was shocking. It showed that if enough mass were packed into a small enough volume, space-time would curve so intensely that nothing, not even light, could escape. This was the birth of the black hole, though the name would not be coined until decades later. In Schwarzschild's geometry lies a strange feature called the event horizon. It is not a surface in the ordinary sense, but a boundary in space-time. Once crossed, escape becomes impossible. Light emitted just inside the horizon can never reach the outside world. For an observer at a distance, the horizon appears as a one-way gate, a place where time itself grinds nearly to a halt. Imagine watching a spacecraft fall toward a black hole. From your vantage point far away, the clocks on board appear to tick more and more slowly as the ship nears the horizon. Signals sent outward arrive ever more delayed, ever more stretched, until finally, they fade altogether. To you, the ship seems frozen at the brink, suspended in time. But to the crew inside, their clock ticks normally. They feel no sudden pause. They pass through the horizon in finite time, continuing their journey inward. The paradox is only apparent, for both perspectives are true within their own frames. This is the essence of gravitational time dilation, taken to its ultimate extreme. Near a black hole, the difference in the flow of time between inside and outside becomes infinite. For those who remain distant, time at the horizon never advances. For those who fall inward, time continues, as always. The geometry of space-time permits no reconciliation, only the recognition that time itself is relative in the deepest possible way. The slowing of time is accompanied by the stretching of light. Photons, climbing away from the black hole, are redshifted endlessly, their frequencies stretched until they vanish from view. The black hole does not emit darkness because it swallows light in the usual sense, but because space-time itself stretches light beyond detection. Time dilation and redshift are two faces of the same geometry, revealing the grip of gravity on both matter and radiation. What is most remarkable is that these effects are not confined to imagination. They are written into the mathematics with a precision as exact as any law of physics. They are consequences of the geometry itself, unavoidable and absolute. To deny them would be to deny the fabric of space-time. And yet, though the mathematics is clear, our intuition rebels. We are creatures who live in gentle fields of gravity, where the slowing of time amounts to billionths of a second. To imagine a place where time halts altogether feels like standing at the edge of myth. But black holes are not myths, they are real, confirmed by observation of stars orbiting invisible companions, by the detection of gravitational waves from their collisions, and by the first images of their shadows taken by the Event Horizon Telescope. They are the ultimate proving grounds of Einstein's vision, the cosmic laboratories where space-time reveals its full power. To stand outside a black hole and watch time stretch is to glimpse eternity in motion. To fall inward is to discover that eternity is relative, that one traveler's seconds can be another's infinities. Gravity here does not whisper. It shouts, commanding time itself to bend until it can bend no more. To imagine the grip of a black hole on time, picture two observers, one drifting far away in the calm of space, the other falling toward the dark abyss. The distant observer holds a powerful telescope, aimed steadily at the traveler descending toward the horizon. At first, everything seems ordinary. The spacecraft falls as expected. Signals arrive at regular intervals. The crew appears to move normally. But as the ship nears the event horizon, strangeness sets in. The signals begin to stretch, each one arriving more slowly than the last. The clocks on board, once in harmony with those outside, begin to lag. The fall appears to slow, the ship hovering as though caught in invisible tar. At last, as the horizon is approached, time seems to freeze. The spacecraft never crosses from the outside perspective. It hangs suspended, red light from its beacons fading into darkness. Inside the ship, the story is entirely different. The crew feels nothing unusual. Their clocks tick steadily. Their hearts beat normally. Their conversations continue without pause. They cross the event horizon in finite time, and no matter how they try, they cannot turn back. From their perspective, the journey is swift and irreversible. The difference between their view and the outside view is not illusion, but a direct expression of space-time's geometry. Time itself is sliced differently for each observer, and neither account is more real than the other. This divergence in perspective is one of the most unsettling features of relativity. It tells us that there is no universal time to which all observers must conform. Each path through space-time carries its own rhythm, and in the presence of a black hole, those rhythms diverge dramatically. To the distant astronomer, the falling ship is frozen. To the crew, it is not. The paradox dissolves once we accept that time is not absolute. Light adds to the spectacle. Photons emitted by the spacecraft climb out of the black hole's gravity, but their wavelengths are stretched ever longer. To the astronomer, the light shifts to red, then to infrared, then to radio, until it fades beyond detection. The ship does not vanish because it falls inside. It vanishes because space-time stretches its signals into invisibility. The black hole cloaks its victims not by swallowing them in the ordinary sense, but by bending time so fiercely that their light cannot reach the world outside. This slowing of time at the horizon is so extreme that it creates the illusion of stasis. Black holes appear to be eternal vaults, with matter and light piled endlessly at their edges. In reality, for the infalling objects, nothing of the sort occurs. They continue inward, crossing the horizon without fanfare. The disconnect between these perspectives is the essence of gravitational time dilation, magnified to infinity. It is tempting to ask which view is correct. Does the ship truly freeze at the horizon, or does it cross? The answer, strange yet inevitable, is that both are correct within their frames. The geometry of space-time allows no single truth about time that all observers must share. Reality is relative, and in the domain of black holes, relativity reveals itself with terrifying clarity. The event horizon thus becomes not just a boundary in space, but a boundary in time. It separates not only regions of space-time, but also experiences of reality. To those outside, it is a surface where time halts. To those within, it is a gateway beyond return. The horizon is both a prison and a passage, depending on where one stands. When astronomers contemplate black holes, they are not simply studying dark objects. They are studying the limits of time itself. The frozen faces of falling travelers, the endless redshift of their light, the divergence of clocks at the edge of eternity. These are not metaphors, but measurable consequences of Einstein's equations. They remind us that the flow of time we trust so deeply can be stretched, slowed, and broken in ways our senses could never imagine. And beyond the horizon, mystery deepens. For Einstein's equations continue inward, describing a place where space-time collapses to a singularity, a point of infinite density and zero volume. Here, the mathematics falters, and our understanding of time itself breaks apart. What lies at the heart of a black hole remains the most profound riddle of physics, where relativity and quantum theory must one day unite. But before we confront the singularity, we must pause at the horizon. For it is here that relativity shows its most cinematic power, where the difference between observers becomes absolute, where the slowing of time ceases to be a subtle detail and becomes the very definition of reality. To linger at the edge of a black hole is to witness the full mastery of gravity over time. Every heartbeat, every oscillation of light, every rhythm of the universe is stretched until it is unrecognizable. From afar, the black hole appears not simply as a void in space, but as a rupture in time itself, a place where the river of moments becomes a stagnant pool. The closer one draws to the event horizon, the slower the flow becomes, until for the outside world, it seems to cease altogether. This is not imagination, but the inevitable outcome of the Schwarzschild geometry. Time dilation is encoded in the very metric that describes the space-time around a massive body. As the radial coordinate approaches the horizon, the ticking of clocks, relative to the outside observer, approaches zero. The mathematics demands it. The experience confirms it. Gravity and time are bound in a dance so profound that the horizon of a black hole is as much a temporal barrier as it is a spatial one. The implications reach far beyond the fate of a falling traveler. They touch the very structure of the universe. Consider light itself. A photon emitted just above the horizon must climb through an almost infinite gravitational gradient. Its wavelength stretches endlessly, its energy dwindling toward nothing. To the outside world, such a photon never quite arrives. The black hole thus cloaks itself, not by obstruction, but by dilation, by the stretching of time so severe that signals are erased from existence. And yet, to the infalling traveler, none of this is visible. Their watch continues to tick, their body continues to move, their seconds continue to pass. They cross the horizon without pause. Time for them flows normally, even as the rest of the universe watches their final signals fade into silence. This duality is the most striking lesson of relativity. Reality is not one but many, each frame of reference carrying its own truth. For black holes, the divergence of truth is absolute. To those outside, time halts at the horizon. To those within, it continues inexorably to the singularity. There is no contradiction, for each account is bound to its observer. The geometry of space-time does not permit a single universal description. It permits only perspectives, and in the presence of a black hole, those perspectives can never be reconciled. This realization unsettles the human mind because it strikes at the foundation of how we conceive reality. We crave a single story of time, a universal chronology to which all moments belong. Relativity denies us that comfort. It shows us a cosmos where time is fractured, where gravity's sculpts separate realities, and where the black hole stands as the ultimate proof of this disunity. And still, black holes are not only theoretical curiosities, they are out there, scattered across galaxies, lurking at the hearts of stellar remnants and galactic cores. We have seen their shadows imaged against the glow of falling matter. We have detected their collisions in the form of gravitational waves, ripples in space-time itself. In these collisions, time dilation is not a distant abstraction, but a cosmic symphony, each wave carrying the signature of clocks slowed by unimaginable gravity. To contemplate these objects is to confront the fragility of our own perspective. On Earth, we live in a place where gravity is gentle, where the slowing of time amounts to nanoseconds, where we can pretend that clocks everywhere keep the same beat. But the black hole reminds us of what lies beyond. It shows us that gravity's power has no upper limit, that time can be slowed to stillness, that eternity can be sculpted into the geometry of space-time. And so, the story of black holes is the story of time pushed to the brink. They are not only regions of collapsed matter, but monuments to relativity's deepest truths. They show us that time is not an absolute stage, but a participant, bent and broken by gravity, frozen at horizons, erased by singularities. From here, our journey must expand outward. For black holes are the extremes, but they are not the whole. The slowing of time by gravity is not confined to their terrifying edges. It is at work everywhere, from the hearts of stars to the depths of galaxies, shaping the flow of moments across the cosmos. To understand time in the universe, we must see it not only in the grip of black holes, but in the quiet pull of countless suns, neutron stars, and clusters of matter that bend the fabric of space-time. The cosmos itself is a landscape of time dilation, a patchwork of rhythms stretched and slowed by gravity. Black holes show us the end of the story. The stars and galaxies show us its vast middle. The slowing of time is not reserved for the terrifying brink of black holes. It is a feature of gravity everywhere, written into the quiet depths of stars, the collapsed hearts of supernovae, and even the vast basins of entire galaxies. To understand this is to see the cosmos not as a stage where one clock marks the passage of all things, but as a tapestry of countless rhythms, each one bent by mass, each one flowing at its own pace. Begin with an ordinary star, not unlike our Sunday. Its mass curves space-time, and though its surface is not nearly as extreme as that of a neutron star or black hole, the bending of time is there all the same. A clock on the star's surface ticks more slowly than a clock far away in empty space. Photons, climbing out of its gravity well, are stretched into slightly longer wavelengths, their spectral lines shifted toward the red. Astronomers detect this redshift in starlight, and by doing so, they glimpse the slow pace of time on stellar surfaces. The effect is subtle, but it is measurable. Proof that gravity bends time not only in extremes, but in the everyday machinery of the universe. Now consider a neutron star, the collapsed remnant of a massive star that has exploded in a supernova. Here, the mass of one or two suns is squeezed into a sphere barely 20 kilometers wide. The result is a gravitational field so intense that time near the surface is drastically slowed compared to time far away. A single hour on the surface might correspond to several hours outside. Were a human able to stand there, though no human could survive the crushing gravity, they would live fewer moments than their twin who remained at a safe distance. To visit a neutron star is to visit a place where the universe insists that life itself must be lived more slowly. Across galaxies, the effect becomes grander still. Galaxies are immense collections of stars, gas, dust, and dark matter, their combined mass-bending spacetime on colossal scales. The flow of time in the depths of a galactic well is different from that in the vast intergalactic void. Though the differences are smaller than those near neutron stars or black holes, they accumulate across billions of years. Clocks in the hearts of galaxies run at rhythms, not shared by the emptiness between them. Even the universe's great structures impose their signature on the flow of moments. This unevenness raises profound questions about what we mean by the age of the cosmos. If time itself flows at different rates in different places, then there is no single universal clock that can describe the whole. The universe is not like a choir singing in perfect unison, but like an orchestra whose instruments play in overlapping tempos, weaving a complex and beautiful harmony. Each star, each planet, each galaxy carries its own beat, and the geometry of space-time ensures that no two are exactly alike. To live on Earth is to live within one such rhythm, set by the mass of our planet, the pull of our sun, and the position of our galaxy in the cosmic web. To imagine other rhythms is to imagine lives lived differently, moments stretched or compressed by the gravity of other worlds. On a planet orbiting close to a neutron star, civilizations might rise and fall in fewer heartbeats than ours. Though measured from afar, their histories would span vast stretches of time. The relativity of time means that the story of existence itself is never told on a single timeline but on countless intertwined ones. What makes this so powerful is that it is not speculation but necessity. Once time is seen as part of space-time, once gravity is understood as curvature, the slowing of time follows everywhere mass resides. It is not confined to special places. It is the rule, not the exception. Every star, every planet, every cluster bends time, and the universe is a patchwork of those bends. The cosmic consequence is staggering. Time does not simply pass. It pools in valleys. It stretches on slopes. It accelerates on peaks. The universe is not a clock, but a landscape, and every traveler experiences a different journey across it. This truth, revealed by Einstein's equations, has transformed our understanding of not only physics but reality itself. And if ordinary matter can sculpt the flow of time in this way, what of the invisible majority of the universe? Dark matter, which outweighs ordinary matter 5-1, curves space-time across galaxies and clusters. Though we cannot see it, we can feel its pull in the motions of stars and the bending of light. If it shapes space, it must shape time as well. The unseen scaffolding of the cosmos is also a hidden architecture of time, stretching and slowing it in ways we have only begun to imagine. From the smallest stars to the largest structures, gravity ensures that the cosmos is a patchwork of times. To ask what time it is in the universe is to ask the wrong question. The better question is, for whom and where? And yet, there is an even stranger influence waiting to be revealed. Gravity slows time, but another cosmic actor, dark energy, appears to speed the expansion of the universe itself, altering the cosmic clock on the grandest scale. If mass and gravity bend time into wells, Then dark energy stretches the fabric outward, pulling the tempo of the cosmos into new rhythms. The balance between these forces determines not only the fate of space, but the flow of time itself. Imagine standing at the surface of a neutron star, a sphere only a few tens of kilometers across, yet containing more mass than our Sunday. The gravity is so fierce that a pebble dropped from a height of 1 meter would strike the surface in less than a microsecond, hitting with energy greater than an atomic bomb. But gravity there does not only crush matter, it also crushes time. A clock on that surface would tick at barely half the rate of a clock far away. For every hour lived by a traveler near the star, 2 might pass for someone observing from a distance. Though no human could survive there, the mathematics of relativity tells us unambiguously how time would falter. Neutron stars remind us that gravity does not need to become infinite to work its spell on time. It only needs to be dense enough to fold space-time upon itself. Now picture the core of a galaxy. Tens of billions of stars orbit together in a gravitational dance held in place by dark matter. The entire galactic well is a basin in the fabric of space-time. Shallow compared to a black hole, but vast in extent. A clock at the heart of a galaxy does not keep exactly the same time as a clock in the void between galaxies. The difference is not dramatic, but stretched over billions of years it becomes meaningful. The universe is older in the voids than in the galactic centers, because time runs differently in each. Thus, even the age of the cosmos depends on where you stand. Astronomers searching the skies can measure these effects in the starlight that reaches Earth. The light from white dwarfs, neutron stars, and massive suns is shifted to the red, not because the stars are moving away, but because time itself is slower at their surfaces. This gravitational redshift is the fingerprint of curved time, visible in every spectrum. In galaxies, the motions of stars reveal the unseen mass of dark matter, but the very presence of that mass also means that time itself is being bent, though we cannot yet measure it directly. The cosmos is a patchwork quilt of clocks, each sewn into the fabric by gravity, each marking a different tempo. Consider, too, what this means for civilizations that might exist elsewhere. If life were to arise on a world orbiting close to a massive star, its inhabitants would experience time more slowly, relative to those living farther away. Their entire history, their epochs of art, science, and discovery would play out in fewer ticks of a distant clock. From our perspective, they would seem to live in slow motion. From theirs, we would seem to race ahead. The relativity of time is not just an abstract truth, but a reminder that the universe is filled with perspectives so alien that they defy ordinary thought. In clusters of galaxies, where gravity binds thousands of galaxies into vast congregations, the effect grows greater still. The gravitational potential wells of these clusters are so deep that they bend light across millions of light years, creating arcs and multiple images of distant galaxies. If light is bent, then time too is stretched. Every photon climbing from the depths of a cluster arrives to us with the mark of slowed time encoded in its wavelength. To study these clusters is to study not only the arrangement of matter, but also the differing rhythms of time that echo across the cosmos. Even within our own solar system, relativity is quietly at work. The sun's gravity bends time so that clocks closer to its surface run more slowly than those farther away. Signals sent from Earth to spacecraft near the sun reveal delays caused not only by distance but by time dilation. Every probe and every mission must account for this if we wish to navigate with precision. The geometry of space-time is not an idea we can ignore when we reach beyond Earth. It is the very medium through which exploration occurs. All of this paints a universe that is not synchronized. There is no universal now, no single ticking metronome that governs all things. Instead, there are countless local nows, each shaped by the gravitational environment in which it resides. A moment here is not the same as a moment there. The cosmos is not a clock, but a vast orchestra of tempos, each bound to the curvature of space-time. And this realization leads to deeper wonder. If gravity sculpts the flow of time, then every great structure in the universe is not only a configuration of matter and energy, but also a sculptor of history itself. Galaxies, stars, planets, and clusters do not merely occupy time. They shape it, bend it, slow it. The universe is a mosaic not only of matter and light, but of moments flowing at unequal speeds. It is a staggering vision, and yet it is incomplete. For while gravity slows time, another force, or perhaps another property of space-time, appears to push the opposite way. Dark energy, the mysterious driver of cosmic expansion, seems to alter the rhythm of the universe on its largest scales. If gravity is the hand that slows time in the depths of stars and galaxies, dark energy is the hand that stretches the cosmic clock, accelerating the expansion of space itself. Time across the cosmos is a fractured flow, drawn out and slowed by every well of gravity it encounters. To stand in the void between galaxies is to stand in a place where moments pass more swiftly than in the hearts of galaxies. To live on the surface of a white dwarf or a neutron star is to live a life where the seconds are rationed more tightly than in the gentle field of Earth. The universe does not share one tempo. It is a patchwork of rhythms, each shaped by mass, each sculpted by curvature. This unevenness changes how we think about cosmic history. When cosmologists speak of the age of the universe, they give a number, 13.8 billion years, as though it were the same everywhere. But relativity whispers that such an age is not universal. It is an average told from our perspective, standing on Earth, within our galaxy. A traveler in the depths of a cluster or floating in the emptiness between superclusters would tell a slightly different tale. Time has not flowed equally in all corners of the cosmos. The story of the universe is written in many parallel tempos. The evidence of this truth shines from the stars themselves. Spectral lines in the light of massive stars and compact objects show the unmistakable fingerprints of gravitational redshift. Photons born deep in gravitational wells arrive to us stretched, announcing that time flowed more slowly at their source. This is not theory alone, but observation, recorded by telescopes and spectrometers, confirmed across decades of astronomy. When we study starlight, we are studying time itself, bent and curved by gravity long before it reaches our eyes. Even light that never touches a star can carry the signature of bent time. As it travels past galaxies and clusters, its path is deflected by the curvature of space-time. These gravitational lenses create arcs and multiple images of distant galaxies, bending not only space but also time. Signals from lensed objects often take different routes, arriving to us with measurable delays. A single cosmic event, like a supernova or the flicker of a quasar, can be seen more than once because time itself has been stretched along different paths. These delays are clocks written into the universe, revealing that even the emptiness between stars is not free of relativity. In this sense, the cosmos is both a map of space and a map of time. Every massive body draws time inward, slowing it, deepening its well. Every cluster and galaxy sculpts the surrounding flow of moments. The universe is not only expanding in space, it is expanding in the diversity of times. To chart the heavens is to chart the different ways time has been shaped across billions of years. This leads us to an even deeper realization. Gravity, the same force that binds planets to stars and stars to galaxies, is also the force that sculpts the very tempo of reality. When we say gravity slows time, we are saying that mass and energy determine not just where things move, but how fast time flows while they move. The flow of history itself depends on the distribution of matter across the cosmos. Every galaxy, every cluster, every hidden halo of dark matter participates in writing the script of time. And yet, gravity is not the only actor. As we gaze deeper into the cosmos, we find that on the largest scales, time seems to behave differently. Still, galaxies drift apart faster than expected, as though space itself were accelerating outward. This mysterious expansion, driven by what we call dark energy, appears to warp the cosmic clock in a way opposite to gravity. Where mass slows time, dark energy stretches it, quickening the tempo of the universe's expansion. Thus, the story of time dilation across the cosmos is incomplete without dark energy. For if gravity is the sculptor that deepens the wells of time, dark energy is the hand that flattens them on the grandest scales. Together, they create a universe where time is not only relative to place but also to the cosmic epoch itself. To understand the future of time, we must now leave behind the wells of stars and galaxies and turn our gaze to the accelerating fabric of space-time, where the flow of moments is shaped not by mass, but by the strange pressure of the vacuum itself. For centuries, gravity was seen as the dominant architect of the cosmos, the force that draws planets into orbits, holds stars together, and sculpts galaxies from clouds of gas. Einstein deepened that vision, showing gravity not as a force, but as the bending of space-time itself, slowing time wherever mass resides. Yet as humanity gazed deeper into the universe, another presence revealed itself, one stranger than gravity and far less understood. Dark energy, the mysterious agent of cosmic acceleration, emerged as a rival shaper of reality. If gravity slows time by pulling space-time inward, then dark energy appears to stretch the fabric outward, quickening the universe's grandest rhythms. The discovery began with a question about the fate of the cosmos. For decades, astronomers assumed that the expansion of the universe, born in the Big Bang, would gradually slow under the pull of gravity. Galaxies might drift apart more sluggishly, and perhaps, given enough mass, the expansion might reverse, collapsing the universe into a fiery end. But in the 1990s, teams of scientists measuring distant supernovae found something shocking. Instead of slowing, the expansion was speeding up. The galaxies were racing apart faster and faster, as though repelled by a hidden hand. This acceleration demanded an explanation, and the name given to it was dark energy. It is not energy in the ordinary sense, like heat or motion. It is a property of space-time itself, a kind of pressure that pushes outward rather than pulling inward, and its effect is profound. While gravity sculpts valleys in the fabric of space-time, slowing the flow of time in those wells, dark energy stretches the fabric globally, altering the tempo of the universe as a whole. To understand this, imagine a vast rubber sheet. Place a heavy ball in the center, and the sheet curves downward, slowing the marbles that roll nearby. This is gravity, bending space-time and stretching time into valleys. Now imagine that the sheet itself begins to expand outward, pulling its threads tighter and carrying the marbles away from one another. This is dark energy, accelerating the stretching of the fabric itself. The marbles are not moving under their own power. The sheet itself is changing beneath them. The presence of dark energy alters our understanding of the cosmic clock. Gravity slows time locally, binding it to stars, planets, and galaxies. Dark energy, by contrast, speeds the expansion of the background itself, giving the universe a faster tempo on the largest scales. This interplay means that time is shaped not only by where you are in relation to mass, but also by when you live in the history of the cosmos. In the early universe, gravity dominated, binding matter together into galaxies and clusters. In the modern epoch, dark energy dominates, driving galaxies apart and reshaping the cosmic flow. This duality gives the universe a layered rhythm. Near stars and planets, time bends inward, slowed by gravity. Across the cosmic horizon, time is stretched outward, hurried by dark energy. The result is a universe where time itself is not one simple river but a confluence of streams. Some slowed in local basins, others accelerated in the expanding sea of space-time. The implications are staggering. It means that the universe's age, the 13.8 billion years we assign as a single number, is not merely a measure of gravitational time, but also of dark energy's influence. The cosmic clock is not fixed. It is sculpted by both the wells of matter and the expansion of the vacuum. Time, in the universe, is not only relative to place, it is relative to epoch, to the balance of forces that shape the cosmos at any given moment. Thus, As we consider the slowing of time by gravity, we must now confront its counterpart, the stretching of time by dark energy. One bends the local, the other reshapes the global. Together, they write the universe's history, not only in space, but in time, setting the rhythm by which galaxies form, collide, and drift into the darkness. The revelation of dark energy forces us to reconsider the very notion of cosmic time. For if gravity bends the local flow, slowing it near stars and galaxies, then dark energy reshapes the universal tempo itself. The expansion of space-time is not a backdrop upon which events unfold, but a dynamic process that dictates how moments accumulate across billions of years. To see this, imagine galaxies adrift in the cosmic ocean. In the absence of dark energy, their expansion would gradually decelerate under the pull of their mutual gravity. The universe would slow, much as a ball tossed upwards slows under Earth's pull. But with dark energy present, the opposite occurs. The expansion accelerates, as though the ball were pushed higher and faster by an unseen force. This acceleration does not come from within the galaxies. It comes from the fabric of space-time itself, stretching more rapidly with each passing epoch. This stretching has direct consequences for time. In a universe dominated by gravity, the future would be one of slowing expansion, where the tempo of cosmic history gradually eased. But in a universe dominated by dark energy, the tempo accelerates instead. Galaxies race apart. Light from distant systems stretches into longer wavelengths, and the observable universe grows ever emptier as horizons recede. From our perspective, time seems to run faster on these larger scales, pulling events apart and scattering them across an expanding void. Relativity binds these ideas together. If the geometry of space-time dictates how matter moves, then the dynamics of expansion must also dictate how time itself flows. Proper time for observers in distant galaxies is not the same as for us, because the expansion alters the separation of events across the universe. Just as a gravitational well can stretch the seconds of a clock, so too can the accelerating fabric stretch the intervals of cosmic history. The ticking of the universe is not steady but swayed by the invisible hand of dark energy. This interplay is visible in the light of the most ancient objects. Photons from distant supernovae arrive to us dimmer and redder than expected, their journeys elongated by the accelerated expansion. Each photon carries not only the signature of its star, but also the history of the fabric it crossed. The redshift of galaxies, the faintness of supernovae, the patterns in the cosmic microwave background all are records of how the cosmic clock has quickened under dark energy's sway. The presence of dark energy raises unsettling questions about the future. If the acceleration continues indefinitely, galaxies will drift beyond visibility, their light stretched until it vanishes from our instruments. The universe will grow darker, lonelier, and emptier, not because matter has vanished, but because time and space have stretched so swiftly that contact is lost. In such a future, the cosmic clock ticks not toward collapse, but toward isolation, a horizon shrinking inward until only local structures remain. Yet the precise nature of dark energy remains hidden. Is it a constant property of space-time, as Einstein once proposed in his cosmological constant? Or is it something more dynamic, a field that evolves with time, waxing and waning as the universe ages? If it changes, then so too does the fate of time. Perhaps the acceleration will intensify, tearing apart galaxies, stars, and even atoms in a final expansion known as the Big Rip. Or perhaps it will weaken, allowing gravity to regain influence in distant epochs. Each possibility writes a different ending for time itself. What is certain is that dark energy joins gravity as a co-author of cosmic history. Where gravity sculpts the local and slows time into wells, dark energy sculpts the global, stretching the clock of the universe. Together, they create a cosmos where time is not singular, but layered, where the seconds we count on Earth are bound both to the mass of our planet and to the accelerating horizon of space-time. This dual vision of gravity slowing and dark energy stretching forces us to abandon the last remnants of absolute time. There is no universal tempo, no single cosmic metronome. There is only the geometry of space-time, and within it, the interplay of forces that bend, slow, and hasten the rhythm of the universe. The presence of dark energy means that time itself is not only uneven across the universe, but also evolving across epochs. Gravity creates wells in which moments slow, but dark energy stretches the entire fabric, altering the rhythm of cosmic history from age to age. In the earliest moments after the Big Bang, gravity reigned supreme. Matter clumped, stars ignited, galaxies formed, and time was dictated by the relentless pull of mass. Billions of years later, the balance shifted. Dark energy began to dominate, its repulsive pressure overwhelming gravity on the largest scales. The tempo of expansion quickened, and with it, the unfolding of cosmic time changed character. In this sense, the universe is like a symphony that changes tempo mid-performance. The early movement was driven by gravity, slowing and binding, giving rise to structure and complexity. The current movement is driven by dark energy, accelerating and stretching, scattering structures apart. What comes next depends on the true nature of dark energy, a truth we do not yet know. If it remains constant, the universe will continue its outward rush forever. If it strengthens, the tempo will become frantic, leading to the possible tearing apart of galaxies, stars, and even the fabric of atoms. If it weakens, gravity may again emerge as the dominant hand, altering the cosmic clock once more. The fate of time is therefore tied to mysteries we have not yet solved. The measurements we make of distant supernovae and the cosmic microwave background are not only about space, they are about the ticking of the universe itself. Every data point is a clue to how time flows across the largest scales, whether it will continue to accelerate or someday bend toward a new destiny. We are reading the heartbeat of the cosmos, trying to decipher its future in the faint light of galaxies, billions of years away. What makes this even more astonishing is how ordinary our own experience feels. On Earth, seconds pass in steady rhythm. Our clocks, corrected by relativity but still bound to our daily lives, mark time as though it were absolute. Yet those same seconds are nested inside layers of curvature and expansion. They are shaped by Earth's gravity, slowed by the sun's pull, stretched by our galaxy's mass, and expanded by the influence of dark energy itself. Every tick of a clock in your hand carries the signature of forces spanning from local wells to cosmic horizons. To live in this universe is to inhabit a time that is deeply relative, shaped by matter nearby and by energies far beyond our perception. Gravity pulls time inward. Dark energy pushes time outward. Together, they weave the history of the cosmos, a history not written on one universal page, but across countless layers, each with its own tempo. And so we are left with a profound truth. Time is not a passive stage on which the universe performs. It is part of the performance, shaped and reshaped by the very forces that guide the stars. To ask why gravity slows time is to ask how space-time itself responds to matter and energy. To ask what dark energy does is to ask how space-time evolves on its largest scales. Both answers point us to the same conclusion. The flow of time is not fixed. It is sculpted, relative, dynamic, and cosmic in its scope. The more we study it, the stranger it becomes. For gravity and dark energy do not only govern matter and light, they govern the very pace of reality. They tell us that there is no single cosmic clock, only an evolving interplay of rhythms, as though the universe itself were improvising its own music, guided by unseen hands. This realization prepares us for a deeper exploration. If time is so relative, shaped by gravity and stretched by dark energy, What does it mean for us who live within it? Do those who live deeper in gravity truly live less? Is existence itself shortened or lengthened by where one stands in the universe? These are not only scientific questions but philosophical ones, touching the nature of identity, existence, and what it means to live in a cosmos without universal time. The answers lie beyond physics alone. They lie in our willingness to accept relativity, not only as a scientific truth, but as a reimagining of reality itself. And so, as we move beyond dark energy, we must confront the philosophy of slower time, where relativity meets human experience and challenges everything we thought we knew about the flow of life itself. When Einstein first revealed that time is not absolute, the shock was primarily scientific. It overturned centuries of assumptions about space and motion, about the universality of seconds and hours. But the deeper shock, one that continues to ripple even now, is philosophical. If time flows differently in different places, if gravity slows it and cosmic expansion stretches it, then what does it mean to live a life? What does it mean to say that one being is older or younger than another? And can existence itself be shortened or lengthened depending on where in the universe it unfolds? Begin with the simple truth of gravitational time dilation. A person living at sea level on Earth, deeper in our planet's gravitational well, experiences time ever so slightly more slowly than a person living on a mountaintop. The difference amounts to billionths of a second over a lifetime. Yet the principle is absolute. The one closer to Earth's center of gravity will have lived a shorter span of universal time than the one farther away. Multiply this effect by stronger gravity, by neutron stars or black holes, and the difference becomes profound. For someone living on a world orbiting a dense star, their entire history could pass while billions of years unfold elsewhere. Does this mean they live less? From their perspective, no. Their hearts beat normally. Their days pass at the usual pace. Their lifetimes feel complete. Yet from the perspective of the universe outside, they live through fewer moments. Their story is compressed in the cosmic record. This duality is unsettling, for it suggests that the measure of existence is not singular but relative. To ask how long one has lived depends not only on biology but also on gravity. This thought leads us to the twin paradox, a scenario first posed in the context of special relativity. One twin embarks on a high-speed journey into space, while the other remains on Earth. Upon reunion, the traveling twin has aged less, their time slowed by motion. If we place gravity into the equation, the paradox deepens. A twin who lives on a world near a black hole will age far less than one who remains on Earth. The difference is not theoretical. It is a real prediction of relativity. And if such journeys or habitats were possible, the results would be measurable in years, not nanoseconds. What then is age? If one twin feels the passage of 50 years while the other feels only 5, are they truly separated in time? The answer lies in the relativity of experience. Time is not a universal ledger. It is local, written into the path each twin takes through space-time. Both lived complete lives in their own frames, and neither can claim to be more or less real. The paradox dissolves when we accept that there is no cosmic master clock against which all lives must be measured. Yet the philosophical implications go further. If existence itself is relative, if lifespans are shaped not only by biology, but by gravity and motion, then meaning too becomes relative. The value of a life cannot be determined by its length in universal time, for no such universal time exists. Meaning must be drawn from the lived moments themselves, from the rhythm experienced along one's own path. Relativity does not diminish existence. It enriches it, revealing that every path through space-time is unique, every heartbeat shaped by the geometry of the cosmos. And yet, a subtle unease lingers. To know that others may live longer or shorter in comparison simply by standing in different places raises questions about fairness and destiny. Would a civilization orbiting a neutron star, living through fewer universal moments, be somehow deprived? Or would they simply experience reality on a different scale, their tempo slower, but no less complete? Relativity refuses to answer. It offers no universal measure of worth. It tells us only that time itself is plural, and meaning must be found within each frame. This realization challenges ancient ideas of eternity and divinity. For centuries, time was seen as absolute, flowing from a source beyond the universe, a divine clock against which all creation could be measured. Relativity strips this away. Time is not handed down from outside. It is woven from within, shaped by the very matter and energy of the cosmos. The divine is not a master clock, but the fabric itself, sculpted and reshaped by gravity and expansion. In this way, relativity does not diminish the wonder of time. It elevates it. Every place in the universe becomes a cathedral of moments, each with its own rhythm, each a different hymn in the symphony of existence. To live on Earth is to live in one rhythm. To imagine life elsewhere is to imagine other rhythms, other tempos, other ways of being. The philosophy of slower time is the philosophy of diversity, of a universe where existence is never singular, but always relative, always plural, always shaped by gravity's hand. To follow the thought of the twins more deeply, imagine one remains on Earth, while the other descends into the orbit of a black hole. The twin near the black hole feels the steady rhythm of heartbeats and breaths, days and nights passing as they always do. Yet when they reunite, the twin who stayed on Earth has lived through decades, while the one who orbited the black hole has lived through only a handful of years. The mathematics of relativity predicts this outcome precisely. Gravity stretches space-time, and in doing so, it stretches the intervals of proper time along different paths. What we call aging is nothing more than the accumulation of proper time, and proper time depends entirely on the geometry of the journey. The unsettling truth is that both twins are correct. The earthbound twin truly experienced 50 years, and the orbiting twin truly experienced 5. There is no higher authority to reconcile the two. Time is not a universal law written across the cosmos, but a local melody played differently for each traveler. What is remarkable is that meaning is not lost in this relativity. Each twin lived a full and coherent life. Their seconds may differ in number, but their experiences were complete within their own frames. Existence is not diminished by its relativity. It is only made more diverse. This understanding reshapes how we think of age itself. Age is not an absolute tally of years against the backdrop of the cosmos. It is the number of moments lived along one's own trajectory. To say that someone is younger or older becomes a comparison only within the same frame of reference. Across different gravitational wells or different velocities, such comparisons dissolve. One cannot meaningfully ask whether the orbiting twin was robbed of time, for they did not experience any loss. Their life unfolded at its proper rhythm. The universe does not grant or deny moments. It shapes them relative to each path. Philosophically, this raises questions about fairness and destiny. In a universe where gravity bends time, some lives are shorter, in cosmic measure, than others. Civilizations orbiting dense stars may see entire histories unfold while the rest of the universe advances by billions of years. Yet for them, history is complete, lives are full, meaning is preserved. Relativity teaches us that value cannot be measured by a universal clock. Meaning arises from within the experience itself, not from its length when compared against an external scale. This realization also reframes the ancient human longing for immortality. If time is relative, then eternity itself is relative. To fall into the orbit of a black hole is to stretch moments outward, to slow one's tempo against the rest of the cosmos. To travel near the speed of light is to extend a lifetime relative to those who remain behind. Yet these extensions are not truly immortality. They are shifts in rhythm, exchanges between one clock and another. Relativity does not promise escape from time. It promises only that time is malleable, that its flow is sculpted by the geometry of space-time. And so, the philosophy of slower time becomes a meditation on existence itself. We are accustomed to thinking of life as a path measured by a single scale of years and centuries. Relativity dissolves that scale. Life is a path through curved space-time, and every path has its own tempo. There is no universal measure of completeness. There are only local rhythms, each one valid, each one sufficient. This perspective is humbling. It tells us that our lives on Earth are not the standard of reality, but one among many possibilities. We live at a tempo, shaped by Earth's mass, by the sun's pull, by the galaxy's well, and even by the expansion of the cosmos. Others, if they exist, may live at different tempos, slower or faster, longer or shorter, in cosmic comparison. Yet their lives, like ours, are complete within their own frames. Relativity is not only a physical truth, it is a philosophical liberation, a reminder that existence is not bound to one clock, but to many. In this sense, relativity echoes the diversity of the universe itself. Just as stars come in many sizes, galaxies in many shapes, and worlds in countless forms, so too do lives come in countless tempos. To be is to live within one such rhythm, to find meaning in the moments it allows, regardless of how they compare to others. The slowing of time in gravity wells and the stretching of time in cosmic expansion are not limitations. They are expressions of the richness of existence, proof that the universe is not monotonous, but endlessly varied in how it grants the flow of life. The deeper we follow relativity, the more it strips away the last illusions of universal time. For millennia, people imagined that the flow of moments was the same everywhere, a divine current that moved creation forward. Days were thought to rise and fall in unison, years to mark themselves across the cosmos with steady rhythm, and eternity to be an unbroken line. Einstein shattered this vision, revealing a universe where time is not singular but fractured, not imposed from above, but sculpted from within. Gravity is the great sculptor, slowing time in its wells, stretching the ticks of clocks and the beats of hearts. Dark energy is the counterpoint, hastening the expansion of the fabric, quickening the tempo on the largest scales. Together, they leave us with a cosmos where every place carries its own rhythm. There is no master clock, no universal present, no single measure of the past. Instead, there are countless presents, countless pasts, countless futures, each bound to the paths that matter and energy trace through space-time. This truth unsettles because it touches something primal. To live is to measure, to count moments, to mark the span between birth and death. We crave absolutes, for they seem to promise meaning. If life is shorter in one place and longer in another, if time is not the same for all, then what does it mean to say that a life is full? Relativity gives us no cosmic guarantee. It tells us only that a full life is one lived within its own rhythm. Completeness comes not from cosmic comparison, but from local experience. And so, the philosophy of slower time becomes a philosophy of humility. We are not the center of a universal clock. We are one tempo among many, shaped by the mass of our planet, the pull of our star, and the geometry of our galaxy. Our years are not absolute. They are relative, stitched into the fabric alongside billions of other rhythms. To live is to accept this relativity, to embrace that our meaning is local, not universal. This challenges ancient myths of eternity. Religions and philosophies once spoke of time as unchanging, flowing from eternity past to eternity future. Relativity shows instead a cosmos where eternity itself is relative. To linger near a black hole is to stretch moments outward, to approach a kind of temporal infinity compared to the outside world. To drift into the accelerating cosmos is to lose contact with distant galaxies, as though they have slipped into another eternity altogether. Eternity is not singular, it is many, fractured into frames of reference. Yet in this fragmentation lies beauty. The universe is richer for its multiplicity of times. Each star, each planet, Each observer carries its own tempo, and together they form a cosmic symphony of rhythms. There is no need for a universal measure, for meaning arises from the harmony itself. Just as music is not diminished by having many instruments, reality is not diminished by having many times. It is enhanced, made profound by its diversity. As we approach the final truth, we see relativity not as a denial of meaning, but as its expansion. Time is slower here, faster there, sculpted by gravity and stretched by cosmic expansion. Life is shorter here, longer there, not in worth but in rhythm. Eternity itself is not one but many, each bound to the geometry of existence. And in this realization we are prepared for the final step. For if gravity slows time, if dark energy stretches it, if relativity dissolves the universal clock, then what is the ultimate answer to the question? What is time? And why does gravity hold it in its grip? To find that answer, we must gather the strands of physics and philosophy alike and step into the closing chapter of our journey. All along this journey, we have asked a question that seems simple yet contains the weight of the universe. Why does gravity slow time? We have followed its traces from the everyday experience of steady seconds, through the revolution of Einstein's vision, into the warped geometry of black holes, across the patchwork of stars and galaxies, and into the accelerating sea of dark energy. Each step has peeled away an illusion, each step revealing that time is not what it seems. Now, at the end, we must weave the strands into a final answer. Gravity slows time, because time is not separate from space. Together they form space-time, a fabric curved by mass and energy. Clocks measure proper time, the rhythm along a path through that fabric. When gravity bends space-time, it bends those paths, stretching the intervals between ticks. The slowing of time is not a force applied to clocks. It is geometry itself, the shape of the universe telling matter how to move, and matter, in turn, shaping the flow of moments. This truth, though abstract in words, is as real as the pull you feel standing on Earth. We live our lives inside Earth's gentle well of time, slowed ever so slightly compared to empty space. Astronauts orbiting the planet live through seconds that tick differently than ours, though the difference is minute. Near a neutron star, the difference would be profound. Near a black hole, it would be infinite. Gravity does not simply pull on bodies, it pulls on time itself, sculpting the very rhythm of reality. Every observation confirms this. Gamma rays shifted in the Pound-Rebka experiment. Atomic clocks ticking differently on mountaintops and in valleys, GPS satellites correcting for Earth's curvature of time. Starlight stretched from massive suns. Galaxies lensed across clusters. Signals slowed in the void. All are proofs that time bends with space-time. Relativity is not a theory awaiting confirmation. It is the foundation upon which technology and astronomy both rest, as solid as any truth we know. And so, the answer is both simple and profound. Gravity slows time because space-time is curved, and clocks measure the path through that curvature. Yet to stop there would be to miss the deeper meaning. The deeper meaning is that time is not universal. It is local, relative, sculpted by the geometry of the cosmos. To live is to walk a unique path through that geometry, to carry a tempo that is yours alone, shaped by where you stand and how you move. This realization changes how we see ourselves. We are not passengers in a universe with a single clock. We are participants in a universe with countless rhythms, each one as real as the next. Our seconds are stitched into Earth's well, into the sun's pull, into the galaxy's basin, into the acceleration of dark energy itself. Every tick of a clock is a signature of the cosmos, a moment bent and stretched by forces beyond our sight. At the edge of this vision lies a truth that borders on the poetic. Gravity does not merely shape the destiny of stars and galaxies. It shapes the destiny of time. The deeper one stands in its grip, the slower the universe passes by. A traveler near a black hole lives in a slowed eternity while the rest of the cosmos races forward. A civilization in the void may live in a swifter flow of moments than one bound to a dense cluster. Reality itself is plural, a vast symphony of tempos, with gravity and dark energy as the conductors. This is the ultimate answer. Time slows in gravity not because of a hidden force, not because clocks are faulty, but because time itself is woven into the geometry of space-time. The cosmos bends, and time bends with it. The mystery is not in the bending, but in the fact that there is no single time to begin with. Relativity reveals a universe where reality is richer than absolutes, where truth is plural, where existence is a patchwork of moments, lived differently by every observer. And so we close with the vision that Einstein gave us, tested and confirmed across a century, now etched into the very starlight we see. Gravity does not only pull on matter, it pulls on time itself. The deeper you stand in its well, the slower the universe passes you by. To grasp the ultimate answer more fully, we must return to the experiments that proved it beyond doubt. For centuries, time was assumed to be absolute, a steady background, unshaken by the forces of nature. But relativity is not a philosophy alone. It is a science that must be measured, and measure it, we did. In 1959, the Pound-Rebka experiment lifted gamma rays only a few stories up Harvard's Jefferson Tower. The rays were shifted ever so slightly by Earth's gravity. Their frequency stretched because time itself ticked differently between the basement and the rooftop. It was the first precise demonstration that gravity dilates time, not in theory, but in the everyday pull of Earth itself. From that moment onward, Einstein's vision was no longer speculation. It was fact. Decades later, atomic clocks carried to mountaintops and flown on airplanes confirmed the same truth. Their hyperfine vibrations, the most reliable ticks ever crafted by human hands, revealed that a clock in thinner air runs faster than one buried deep below. The effect amounts to nanoseconds, yet those nanoseconds are real. Every second you live is shaped by the height of your dwelling, the curvature of Earth's gravity beneath your feet. Modern technology cannot ignore this. The global positioning system, which guides planes across oceans and cars through city streets, depends on satellites orbiting high above Earth. Their clocks, freed from much of Earth's gravity, run faster than clocks on the ground. Without constant corrections for relativity, GPS would fail within minutes, its calculations straying kilometers from truth. Every moment you navigate with your phone, you are relying on Einstein's insight that gravity slows time. These experiments and technologies are the gentle confirmations, written into laboratories and satellites. But the cosmos itself provides confirmations on a grander scale. The redshift of light from massive stars, the spectral stretching from white dwarfs, the gravitational lensing of galaxies across clusters, all are evidence of clocks slowed by gravity, of time itself bent by mass. Black holes, the ultimate wells of space-time, provide the most cinematic proof of all. As matter falls toward their horizons, it slows to a halt in the eyes of distant observers, light stretched until it vanishes. Time there is not merely slowed, it is all but erased from the outside world. These extremes remind us that relativity is not confined to laboratories or satellites. It is written into the universe itself. Every photon we detect carries a record of the space-time it has traversed. Every clock, from the pulse of a pulsar to the oscillation of an atom, ticks in rhythm with the curvature around it. The universe is not a neutral stage. It is a participant, its fabric bending time as surely as it bends space. This truth also reshapes how we think of cosmic history. The 13.8 billion years we assign as the age of the universe is not a single truth but a perspective, measured from our place within Earth's well, within the sun's gravity, within the Milky Way's basin. Elsewhere, the count would differ. Elsewhere, the cosmos has unfolded at a slightly different tempo. To speak of universal time is to speak of an abstraction. The real universe is a quilt of many times, stitched together by relativity, and yet, the unity of relativity is what gives us the final answer. Gravity slows time because gravity is geometry. It is not a force reaching across emptiness. It is the bending of space-time itself, the stretching of the fabric, the warping of the grid upon which all events occur. When you drop an apple and it falls, it is not pulled, but guided along a curved path in space-time. When a clock ticks slower in gravity, it is not forced to hesitate, but simply following its proper path through that same curvature. The same equations describe both. The same geometry explains all. Thus, the slowing of time in gravity is not an add-on to physics. It is the essence of physics itself. To live in this universe is to live in curved space-time, to carry a clock that ticks in rhythm with the geometry around it. To deny this is to deny reality itself. And so, when we say that gravity pulls on time, we are saying that time is not separate from the cosmos, but woven into it. Every star, every planet, every cluster is not only a mass in space, but a sculptor of time, slowing the moments around it, shaping the rhythm of existence. Gravity is not only the architect of matter, but of history itself. To close this journey, we must let the science merge with the wonder it inspires. Gravity, slowing time, is no longer a hypothesis, no longer a curiosity in equations. It is the living truth of the cosmos, confirmed in laboratories, inscribed in the skies, and etched into the very technology we carry in our hands. But the deeper truth is not only scientific, it is existential. It tells us that reality itself is not fixed but fluid, not absolute but relative, not singular but plural. Stand on Earth, and your seconds are shaped by its mass. Climb a mountain, and you live ever so slightly faster than those below. Drift in orbit, and your clock gains still more seconds. Fall toward a neutron star, and your minutes become hours to those outside. Approach a black hole, and the universe beyond races ahead, while your own heartbeat continues at its steady pace. Gravity does not just guide your steps, it bends the rhythm of your life. This relativity is not tragedy but majesty. It shows us that we are woven into the cosmos more deeply than we ever imagined. We are not passengers moving through time as if it were a neutral river. We are participants in time as sculpted by space-time itself. Every moment of existence is shaped by the geometry of the universe, by the invisible curves of gravity, by the vast expansion of dark energy. To live is to walk a path through this geometry, to carry a rhythm that belongs only to your journey. And so the ultimate answer is this: gravity slows time because gravity is the curvature of space-time, and time is part of that fabric. There is no separate river of moments untouched by the cosmos. There is only space-time itself, bent by matter and energy, guiding not only the paths of planets and stars, but the ticking of every clock, the beating of every heart. The implications reach beyond physics. They touch the meaning of existence. There is no universal now, no master ledger of past and future. There are only local nows, stitched together by relativity, each one as real as the next. Time is plural, not singular. Reality is a symphony of tempos, each shaped by gravity's hand. We may long for absolutes, for a clock that rules all, for an eternity that is the same everywhere. But the universe offers us something richer. It offers us diversity, a cosmos where time itself is alive, flexible, responsive. A cosmos where eternity has many forms, and where meaning arises not from universality, but from the fullness of each local rhythm. As we look to the stars, we now see them not only as points of light, but as sculptors of time. Each star bends space-time. Each galaxy deepens the cosmic quilt of moments. Each black hole freezes time at its edge. Even the emptiness is not empty, for dark energy stretches the fabric outward, shaping the tempo of the universe itself. The cosmos is not a stage on which time unfolds. The cosmos is time, woven and sculpted by the same forces that give it form. So let us end where we began, with a question. Why does gravity slow time? Because gravity does not only pull on matter, it pulls on time itself. The deeper you stand in its well, the slower the universe passes you by. And in that slowing lies the final truth. Time is not a background, not an absolute, not a gift from beyond. It is the very fabric of existence, curved by the weight of stars, stretched by the breath of the cosmos, and lived uniquely by every traveler who moves within it. This is the universe revealed by relativity, not a clock ticking in unison, but a symphony of rhythms, not a single eternity, but countless eternities, not a stage beyond the world, but a fabric woven from the world itself. To live is to live in curved time. To die is to return to it. And to know this is to glimpse the ultimate majesty of the cosmos, that even time, the thing we thought most absolute, is part of the dance.